International Conference on Communications, Circuits and Systems remotely in Wuhan, China, and it's about quantum cryptography. I've been a panelist at the QADC Quantum and AI Use Cases earlier this year, and a regular speaker in the Quantum AI monthly series by Biblioteca Alexandrina and iCafe. Okay, and I'm proud to say that last year in November, I attended the IBM Quantum Developer Conference that was in Poughkeepsie, and I've been invited again. This time it will be in Atlanta in on the 14th and 15th of November. So it's a privilege. For more details, please check out my LinkedIn profile. Okay. So the topic of my presentation is to introduce you to an overview of the so-called sample-based quantum diagonalization algorithm. And I will illustrate this with Jupyter notebooks that I published on GitHub. It's a public GitHub repo, so I will refer to that in a few minutes. So first of all, this is the agenda. So I will frame my presentation around quantum-centric supercomputing, and then introduce SQD, and highlight two very promising proof of value, which has been achieved by IBM Quantum. By the way, my presentation is as President Molket SAS. I'm also a Qiskit advocate, but this presentation is and my ideas are really mine. And but of course, being a Qiskit advocate means that I've got a very good view of IBM Quantum and the Qiskit community. Okay, I just wanted to make that clear. Then we will illustrate those use cases with a demo. Okay. First of all, what is quantum-centric supercomputing? So IBM Quantum, together with Pascal, have put forward their vision that the future is combining high-performance computing, HPC, with quantum processing. And it's called quantum-centric supercomputing. And they put forward their view that this is the way to achieve near-term quantum advantage in chemistry, material science, and other scientific applications. Okay. What is a quantum-centric supercomputer? Well, no surprise, it's comprised of quantum processing units, QPUs, graphical processing units, GPUs, and also CPUs to unlock the next generation of computing. So it's an architecture, and it's also a tight integration of the best of breed of what we have today. Okay. Let's illustrate. I've selected this definition of sample-based quantum diagonalization because it doesn't require any knowledge or any expertise in chemistry. SQD is, well, first of all, is designed as a chemistry simulation technique, but recently it has been used in other fields. But first, it is a chemistry simulation technique. The way it works, it uses the quantum computer to extract a noisy distribution, noisy because at the current stage, the quantum processing units, they are not yet error corrected. So the output, the probability distribution that we get out of these quantum processing units are noisy. That means there are errors. And in the case of chemistry, it's sampling possible electronic configurations a molecule in the form of bit strings. So on the left-hand side, it's illustrated. By the way, there is a glossary at the end of my presentation. So LUCG is explained. LUCG circuits, it is the ansatz, the quantum circuit that is chosen to be a good compromise in terms of being able to hopefully reproduce the behavior of a molecular system, but also being efficiently that it can be run efficiently on the currently available quantum processing units. And so it starts. FFSIM is a new, well, fairly recent software package. We don't use Qiskit Nature for SQD. So the idea is that starting with an ansatz, quantum circuit, there is an iterative correction, which is entirely on the classical part, typically high-performance computer, or in the case of small molecules, could be a laptop. Okay, and that's the main difference with variational quantum eigensolver. That is to say, the iteration is only on the classical side. So, and there is post-processing, which is akin to error mitigation, but a smart error mitigation, which leverages the knowledge of the system. And in the case of chemistry, there are a lot of symmetries, which makes it possible to mitigate errors, leveraging this knowledge of symmetries in the molecular systems. So there is hope that for large enough noisy quantum computers with low enough error rates, this is what we have at the moment. We say, for example, IBM Torino, which is available via the free plan on the IBM cloud, 133 qubits, and error rates which start to be really interesting, that it is now possible to run quantum circuits with depths of a few thousand 2-qubit gates, which is quite impressive. So the claim is that even with currently available quantum processing units, if they are large enough, there is the potential to perform more efficiently than classical approximation methods. Okay. This is, I won't go into details, but this is the detailed view, zooming in on the post-processing. The post-processing, as I said, is kind of error mitigation. And so the key idea with SQD is to break up the otherwise almost intractable quantum diagonalization, because it would be too big, the matrix would be just too big, into smaller chunks. And this is the idea of subsampling, sampling not from the whole distribution, but from samples. And for each sample is solved accurately and classically by diagonalization. And then it's clever because then it's very easy to think about subsampling and breaking up, but it's more challenging to recombine the results into something that makes sense. And the post processing not only does that, but it can detect errors and fix them. And that is based on the knowledge of the behavior of the molecular system in particularly symmetries. Okay, so this is the way it works. So I think it matters to point out the added value of this approach as compared to pure. There's no such thing as a pure quantum algorithm, because there is always the preparation and then the post-processing. But the last couple of years, much attention has been devoted to so-called variational quantum algorithms, in particular VQE, variational quantum eigensolver. And this VQE algorithms are also covered in my book, Quantum Chemistry and Computing for the Curious. Um, the ugly truth is that it is, unfortunately, at least for chemistry, theory and practice has shown that there is no hope to get meaningful results with fairly large molecular systems with just VQE. On today's quantum processing units for the ion sulfur cluster simulation, it is estimated it would take 3 million years, so practically intractable. Now, even on fault-tolerant quantum processing units, which we don't have, the best algorithm, quantum phase estimation, would still require 13 days continuously running on a fault-tolerant QPU, which seems to be quite ambitious to be able to run without interruption. Because, as you know, for those who are not too familiar with quantum computing, um, as soon as you make a measurement, then the state is measured and it's one out of several possible outcomes. And so if there is any event happening during the competition during those 13 days, then unless it has been designed for that, because there is so-called mid-circuit measurement, then that's it. You have got to start from the beginning because the competition is corrupted, right? So it's quite challenging to imagine running a computation on a fault-tolerant quantum processing unit for that long, 13 days. The good news is that SQD, within a quantum-centric supercomputing framework, only takes 2 hours. And so that's what IBM, in collaboration with Cleveland Clinic in the United States and Riken University in Japan, where they host the largest high-performance computer in the world, Fugaku, together, and that required good, if not outstanding, collaboration, a multidisciplinary team. They managed to simulate the ground state dissociation of the nitrogen N2 molecule, and also these clusters, ion sulfur clusters, with SQD in just 2 hours. And so you see, this is an illustration of the value of both quantum-centric supercomputing framework, and in particular, in that context, the SQD algorithm. So really combining the best of what we can have today with the most powerful supercomputer in the world, Fugaku, and one of the best, if not the best, quantum processing unit. Okay. There is another very interesting use case. This time, IBM in collaboration with Lockheed Martin, and they have successfully conducted chemistry simulations with SQD, in particular to simulate the dissociation of the ground state triplet and first excited single states of the methylene molecule CH2. And their study is relevant for not just combustion chemistry, but also for interstellar. And it's worth mentioning that in outer space, chemical reactions happen that cannot be replicated or even occur on Earth. So it's really important to be able to model these in theory. So on the left-hand side, you see the quantum-centric supercomputing. So the researchers used a 52 qubits quantum processing unit. It's worth noting that nowadays, with the free plan, anyone can access a much, much more powerful quantum processing unit. For instance, the IBM Torino with 133 qubits. And as you know, or should know, when we add 1 qubit to a quantum processor, in theory, the power is multiplied by 2. So there is a huge gap. Um, and so on the left-hand side at the bottom, you see what happens is that there are two different states, the singlet, so-called singlet and triplet states of the same molecule. And basically, what happens is that the outer electrons they have spins, and so there are three different ways on the bottom, the triplet. The electrons occupy different orbitals, 3a1 and 1b1, and they have the same spin up. And the singlet state, the electrons occupy the same orbital, but their spins are opposite to one another. And it turns out that these states, the molecule oscillates between one or the other state, depending on the energy. And so this is illustrated there. There is a so-called first order phase transition when the singlet and triplet states are exchanged. And you see there are several plots there. So there are actually three different simulations: SCI, which is the most precise, CCSD, quite popular, and SQD. And you see there are two in red. There are two plots, one with dots and the other one with these three-legged symbols. And you see that at some stage, at around 1.5 lengths, the length between the carbon and one of the hydrogen atom, the two curves they cross one another, and this is where it's important to have an accurate modeling of this. And you see that with SQD, it's as good as what can be achieved with CI, which is the most expensive, most accurate classical simulation. So this is the energy, and this is the bond length. Okay. So now demo time. I don't know how much time have we got, Brian. Let me check. So the idea, and this is to demonstrate on a laptop that we can replicate the 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 first simulation, which is the CH2 molecule in a 631G basis set, which is a fairly good basis set. So I will now move on. I will have to stop sharing and we share again, but this time, okay. This time with the, so how much time have we got? Okay, I think we have got enough time to do an interesting presentation. So I will share again, but this time I will share my, hopefully it will work, my, yeah, I will, oops, no, I want to share, I will share the whole screen, I think, because otherwise it is difficult to share. Okay, so let me get out of this presentation. Yes, so this is the window of my Jupyter notebook, and I've got a Gradio interface which makes it easy to configure. So this is the Gradio interface. So it's possible to with these buttons to load a configuration from a JSON file, so from a previous experiment, and then to run it. It takes about 10 minutes, so in the interest of time, I will just show you the result, but you can check on the repo, it's shared. And so there are a few things. So the basis set, it's explained in the glossary. It's a set of functions, basically, which is supposed to mimic the behavior of a molecule, and there's a large number of basis sets. One of the most popular is so-called 6-31G. As to compute the exact energy classically, this is the atom configuration CH2, okay? And there are these numbers, they pertain to the distance between the different atoms in the same molecule. Symmetries, this is very important. And so the different symmetries. So the interface lets you present this. The spin, the number of frozen orbitals, so the limit on the number of configurations. So these are parameters that quantum chemists are supposed to master really well. And so in that case, we have loaded a JSON file from a previous run. And then on the save configuration and run simulation, I got in about 10 minutes on my laptop with 32 gigabytes memory, I got the
Just
exact
carry,
energy.
just carry on. You can go to quarter past. All right.
Uh, and and then this is the output. So we got the in a few iterations, the energy error is within the so-called um, chemistry accuracy, which is 1 millihartry. And we have got the average occupancy per spatial orbital on the orbital. So this is the right answer. What's amazing, it has been done on a laptop. Okay. Um, I can also show you the same, but this time for the triplet. Can you see my screen? Yes. So for CH2 triplet, it requires a bit more effort, and the outcome is different because the triplet, the external electrons, they do not share the same orbital. So this is a successful simulation, and it was achieved on a laptop. So for those of you who are not too familiar with quantum chemistry, there is a glossary of terms, okay, and there is also an extensive bibliography. Okay, so that concludes my presentation. If there are questions, I'm open, available.
Okay. Can you just go back to the first slide that you shared? I think it
Yes.
has your work, your book, the book that you published. I think
Okay, sure. Let me share again. Um, okay, just bear with me. Partager. Okay. Okay. So there we are. So this is the book Quantum Chemistry and Computing for the Curious. The lead is Dr. Sharkey.
Because it's hiyo ESP32 no imekuwa of very low quality. There's one that behaves like the nanos. Yeah, yeah. Kitu center kuzimeka. Kuna USB hapo. Screen shot.
So what's worth mentioning about the book is that anyone who purchased the book is entitled to access a set of complete Jupyter notebooks. Complete means that has got text and nice LaTeX formulas, images in color, and of course the code. So in other words, there is a set of so-called complete component Jupyter notebooks which lets you replay all the examples written in the book. And even better, I do my best to maintain the code to work with the latest versions of Qiskit Nature and Qiskit. And on a public repo by Pact Publishing, there is a so-called reduced set of Jupyter notebooks. That is to say, there is the text is limited to the chapters, but you have the whole code. And again, I maintain, I think in a clone repo, I maintain so the public repo is public, can be accessed for free. You only have access to the code. So for each chapter, you've got the code for the examples. And I've got a clone repo, a forked rather repo, sorry, forked repo, where I've got the the code which has been maintained to work with the latest version of Qiskit. There has been a lot of changes in Qiskit Nature. I'm not even sure that today Qiskit Nature works with the latest version of Qiskit. It's worth mentioning that the content is still of interest because it shows how to use variational quantum eigen solver. Yeah. Should I? Any other question?
Yeah, is it okay if I share with the audience at a point your work, because I've already been going through your work several times. You've been seeing me sharing your work previously with Dr. Shaki. Is it okay if I share with the Qiskit attendees this season?
So yeah, you're welcome. I will share with you a link to a PDF version of my presentation. And yes, and by the way, yes, anyone can reach out to me on the Qiskit Discord, whether you're a Qiskit advocate or not. But I mean, I receive quite a lot of messages, so unfortunately I cannot. But yeah, and you're welcome to reach out to me, and again, I will share with you, Brian, the link to the PDF version of our presentation. Any other question? Any other?
Oh, not really numbers. Oh, C6.
All right.
Well, exactly.
So if there is no question, I just want to thank Brian and all the organizers of this Qiskit Fall Fest. I will try and attend the other events as a participant. But thank you so much for having me. And
The entry level. Entry level now. Advanced skill. The country has a do at is additional products coming with a lifestyle. Yeah, you can now on board already.
All right, Alan, is it okay if I invite you over on 31st? That's the closing day when Qiskit Fall Fest is ending. Is it okay if I invite you over on 31st October to give another series of talk? Mostly on your previous.
Brian, I cannot at this stage commit that would be available, but I welcome you inviting me because I've got another commitment on the 31st, potentially, and it's not yet decided, but I cannot unfortunately commit that I would be available on the 31st, but I might be. But so I welcome you inviting me, but I will let you know whether I can. If it is only participating, then if there is another event at the same time, maybe I could have. I could be in a superposition of states, but if you expect me to be a speaker at this stage, I cannot commit. No, but by 31st, I should be able to let you know. Okay.
All right, that's okay. So I'm admitting our next speaker, Alberto Maldonado, who works with IBM. So I'm going to admit him to the call, and he'll carry on. Thank you so much, Alan.
Thank you for having me. Goodbye.
All right, everybody. Our next guest is Alberto, and Alberto works with IBM. I hope all of you are registered through the website, and you already read something about him, his profile. So Alberto, can you just carry on?
Yeah, can you hear me? Yeah, okay. Let me check if I can share my screen. Yeah, okay.
Yeah, sure, you can see it. Have you shared yet? Let me just check.
So you can see my screen right now. My presentation, my slides. I think it's okay, right? You tell me when I can start. Can you hear me?
Yes, we can hear you.
Okay. So I will start. It's okay. Okay, I think it's yes. Well, yeah. Alberto Maldonado Roma. I'm a quantum computational scientist in IBM Quantum. Yes, I want to try to explain a little things about quantum computing, but I was more focused in the activity for the hardware. So I need to start to explain about what is quantum computing, or what is the relevant part of using a quantum computer. So right now we are need to thinking more in quantum because characteristics of the problems we have right now in the world try to understand and to explain the characteristics is more necessary thinking in the capacity to understand in the quantum computer. So why is necessary? What is the relevant part of the use of quantum computing? Initially, we can understand we need a quantum computing because certain problems in the nature about chemistry or take a certain decision like a quantum binary optimization decision or try to understand more the AI in certain general things about how can we improve the performance, the characteristics to do a better decision about certain learning ways. So about all of this way, we are using a quantum computer and identify is possible to understand, possible to get at certain problems where we are considered complex in a classical computer, even using GPUs, TPUs, FPGA, and in a quantum computing for the nature of the characteristics for the qubit, we can design the problem and try to get the same answer and using this kind of computer. So in 2023, in IBM Quantum, we identify exist certain methods, certain characteristics when we can obtain the quantum utility. Quantum utility, that means is we can obtain in a quantum computer a program, a model, a software, an algorithm, where we can identify for a specific use case improvements comparable with the classical part. Is for example, we can mention is like you have in a imagine you are for a company, you have a certain problem, try to improve even 1% is a good result because that means like for the data information they got is not just one, it's like millions of the information and try to improve the solution or detect what is like a fake data versus something is a really good one. So in this case, we are trying to do that one. The next steps we are trying to do is the error mitigation and the error correction. Sorry. The error mitigation is try to do a post-processing information when we are trying to do during the hardware in the quantum computer, and the error mitigation is this kind of techniques where we are trying to do improves the codification and try to improve the information for the quantum computer during the like for example, let's like try to do this kind of correction ways, like try to do average information for multiple qubits, try to working with ancillary ones, when try to do this one obtain the average value, what is the correct one. So all of these techniques, we are trying to improve the hardware because at this moment we are working with the NISQ era, the non-intermediate scales of quantum devices. So we are trying to mitigate the error in different techniques we are trying to obtain information for the problems we are getting a better compared with the classical or try to obtain this. So that is the what we are trying to do. So what is the quantum advantage? Is like try to identify for specific tasks where need to identify, evaluate the cost effectively for the characteristic we had at this point and consider it's better try to use a quantum computer. So it's not necessary to thinking all the solutions are necessary a quantum computer. It's more to thinking what kind of the characteristic at this moment is considered a complex problem and we're considered well the point of the state of the art is like was like depends on the state of the art exists multiple solutions, multiple characteristics, and we are very interested in how can use a real devices about quantum computing consider the noise. So depends of this one is identify the solution is optimal to use it even with this noise at this moment. If the answer is yes, and theoretical part is a possibility, so we can try to do that one. So you also remarking what is a quantum computing? Well, we need to remark in a quantum computing we are working because we're using the transistors, and the Moore's law says sometimes we need to reduce the number of the number of the transistor size, but if we're trying to reduce multiple times, in a certain moment we are past the limit in the classical we can say in the classical world and try to move it more in the quantum world because we are trying to understand and try to identify when we are reduced more, we are working with particles. That is the thing we are doing right now. Instead of working with transistor, we are working with the qubit. So at this point, we need to working in that one. But the qubit or the quantum bit, we are working with a certain properties. The properties is like the superposition, the entanglement, and the interference. And this one is very important because depends of the nature of the problem, the characteristics, all of this one, will gain us a good results or take advantage of this one to obtain compared with the classical computing, the same solution. Just of this one, we need to remember what is the bit, so how is working. Well, we're in a block sphere, like the in the left part when we are in the up or in the top part, the zero, and in the left in the bottom part, the one. So we can obtain a certain vector or unitary vector. In this space we are talking is a normalized vector in a is where the model or the amplitude value we obtain is always one of this one. So depends of the characteristic is up, down, or in the middle is the probability when we obtain the amplitude of this model is the probability associated for the specific state. It's like it's always in the top is always the probability zero. Is in the bottom is always one. Is in the between all of them probably could be 80-20, 50-50, 64. So depends of the position of we got it and depends of that when we obtain the information of the scalar values associated for all for one of these combination of the states. Just I need to remark the combination is the 0 and 1. And the other thing is like the quantum circuit. The quantum circuit we're working is like where we can transfer the information of the specific qubit. We can pull in the specific value or the initial value is the C001. And depends on the characteristics, we can try to transform, modify, increase the probability, reduce the transfer probability, or like in this case, just to do a swap of the information of this one. It's like the qubit 0 associated with C0 and qubit 1 associated with C1. But after apply this qubit, just change the information for the qubits, but keeps the information, so don't change. But in the quantum computing during the hardware, this kind of activities is relevant, and we are checking more later in this presentation. So apart of this one of the qubits, we try to do a certain specific state, like I said before, we can associate the state, a zero, or the combination the 0 and 1, or the state 0, Kate, and 1. associated with a certain probability, we can say alpha and beta or A and B. So when we obtain the probabilities associated with this one is elevated to the power of the two, but when it's a complex number, we are considering instead of the same value is the complex conjugate value of this scalar value, and we obtain the probability associated with 0 and 1. So depends on the characteristics of the gates in the quantum computer. We need to identify a zero. Like in the x gate, we can start with zero. When we apply the x gate, we obtain after this one the state one, and the probability gives us the 100% about that one. So the benefit of this one is basically the process we are doing in the quantum computing, and it's just remember the gates is a matrix, so this is a linear operation focused in a matrix way where we are doing all of these characteristics and we are always starting in a zero state, and depends of the value we can try to do a superposition or change the values or do the entanglement. So even with a Hadamard, we can change the information in the same probability for 10, 50%, depends of the nature of the gate. In this case, the Hadamard gate is doing that is part of the job. So the characteristics of the superposition is like we have a basis linear combination, computational, 0 and 1. We are translated in a two and a vector of two-dimensional or bidimensional information in a complex space. We are calling the Hilbert space, and we try to do is like the combination for of this information because depends of this one we can create a vector for this space in any position. So your reminder like says the ket 0 and the ket 1, and we're calling the computational basis in we're create any superposition. Just exist two cases when a is 1, the other is 0 for consequence, and the same way is B is 1, A is 0, and yeah, that is the only cases is we are not obtaining like calling the superposition, but in other cases we always obtain a combination, and it's a superposition. So depends of this one, you just need to remind always when we apply the complex numbers, the conjugate is the probability is equal to 1. So what is the characteristics of the advantage of using the superposition is like we can put in the block sphere, depends on the characteristic, not necessarily 50-50. It could be in another characteristics, and interested is like imagine we are doing a superposition 50-50 for say something and we are putting in the right part. The right part is like positive 0 and 1. So it's like A ket 0 plus B state 1 or ket 1. But what happened we're putting the left is A ket 0 minus B ket 1. So exists a certain difference? Geometry? Yes, but in the probability? No. But what happened there internally when we're
Niko
interested?
nadhani hata ni kubwa.
Sorry?
Anasema
Any question?
That was not intended to be a question, but if I may just ask a quick one, right?
Yeah.
When you are doing quantum simulation and you have a block sphere like this one you have here, right? There's
Yeah.
part where we always do a partial trace, right?
Yeah.
Are there some
Yeah.
dangers of losing some data when you do partial traces?
Depends on the characteristics of the hardware. The idea is like, yeah, when we are applying in a real hardware, the gate, we can lose a certain information, but right now the information for the gate is kind of small, depends on the fidelity of this one. So right now in a 1 qubit gate is the lost information is not like a big deal. The problem is when we are working with 2 qubit gates. But yeah, we lost like 0.0001 for something right now in real hardware. So the idea is, yeah, depends on the characteristics of the amplitude where we are trying to obtain is the same information. And like you say, yeah, probably we're interested in what is the variance for we're doing, I don't know, 2 degrees of difference of the angles in the certain position. That could be more complicated. But yeah, the other question is depends of the things you are doing. It could be a big deal or no. So I hope I answered your question. And continue with that one. Just to remember, depends on the characteristics for the geometry or the characteristics for the angle. We try to do certain information. It could be benefit for us, yes. And the other thing I try to say is like some cases we're interested in the geometry, or some just cases we're interested in the probability. Depends on what you want to do. So it's important, relevant, ask us what is the characteristics and depends where are you looking or what is the kind of the algorithm you are doing, because exists multiple ways where you're doing is focusing the probability or focusing the expectation value when we're following for the geometry of the hardware. So one of the things we are trying to do is the entanglement. Entanglement is the characteristics when we are working with the hardware and try to do this kind of connection between two qubit gates. And what I try to do is like do this kind of connection multiple gates, well, multiple gates with this at least two qubits, and at a certain state we cannot to decompose in one qubit case information. For example, you look in the left part where have this a roadmap for the specific hardware is the real connection with the qubit, and we're just focusing the qubit 4 and qubit 11 when we are trying this connection physically between both of them. What is the thing we are trying to do entanglement or no? Is like we're entanglement where we can do decompose the information. Well, it's not entanglement, we can decompose. If it's not possible, is we're calling this entanglement, and this is not a processing we are doing in the classical computing, and this is the check. If you see the first one, we can separate the qubit left with the qubit right, because the qubit left is always 0, and the right is in a superposition in the square 2 over 2, because if we are apply the model is 2 over 4, what is 1 over 2, what we can translate is 50%, and the for consequence is 50% too. So after
So,
that one we're doing 50-50. Yeah.
yes, I had a question. Why are we using two?
uh,
Why the square of 2/2?
just is an example for say what is a superposition is just for example.
Oh, just an example. Okay, thank you.
Yeah, but this is not necessary. It could be other way. But the thing is like depends of this superposition. We know this is 50% and this is 50%. But what happened here? Is two state. We can separate this one in one state. That means 100% is zero, and this one is the 50%. So when we modify the 50% for these two states, just doing this is entanglement. But what happened here? We can decompose the left qubit with the right qubit. That is impossible because this is 50% too, and this is 50% too. How can we can decompose in one qubit gates all of both of this one? It's impossible. That happened with the third example. Is 50% here and 50% here, but here is not 50%. How can do that one? Well, exists the superposition on the Bell states. This is example, the tier one is when we're just using the Hadamard and the CNOT gate is the two qubit gates when we're connect, in this case, the qubit 4 and the qubit 11 in a real cases. And the thing is like, we can don't write this way in a product of that's two single qubit gates. The first one, yes. And I call you, this is 50-50%. But here is, well, it's impossible to decompose. So you're remarking in a quantum computer, well, yes. It's important to tell what is entanglement, what is the catalytic, the supposition to create this new state when we're working during the quantum computing. How can do that one? How can we deal in the hardware and try to translate this information in this way? So we need to operate or create information using the quantum gates. Classically, we are using the logical circuits when we are authentic operators, the add or not, XOR, or we are creating a more complex set of the variants using these two basic in a more complicated like XOR than AND. But what happened with the quantum circuit is just a matrix when we are doing these irreversible gates, when we are trying to change the quantum state, depends on the number of the qubits, we can create one qubit gate or two qubit gates. And when we try to connect all of them, we can create multiple states, and we are create the superposition, the entanglement states, and we create states which is not possible with the classical computing. And the interesting things, we can even create the positive, negative, real, imaginary uh, values for the quantum states. So we are not say just one specific value. And the characteristic is like, well, if we are trying to work in like in a low level, like a classical computer, what is the benefit? Well, in a quantum computing, we can compute with the caffeine molecule. In a classical computer, is complicated. Try to uh, yeah, programming this part because we are, you know, we are with zero.
Um,
Okay.
I had a question.
Yeah, it's kind of nice. Who is the person give me questions?
Uh,
Okay.
I
Uh,
have a question.
yeah, yeah, yeah.
How do My question is, how do these quantum gates differ from the classical just logic gates?
How can do that one?
How are these quantum gates differ from the classical logic gate?
It's not necessary. Just the classical logical gates is just they working with AND or not an AND because that is working in one group. The one group is just two operators, AND and OR. But in quantum computing, we're in a Hilbert space, so we had more complexity properties compared with the Boolean group. Yeah, with the Boolean group. So in this case, we had metrics. The Yeah, we have this metrics for the distance. So we are properties, normalization, we are characteristics. So we have the X gate, what gate, the police gate, the two qubit gates, CNOP, control C, SWAT gates, and we can create depends on
Did we lose you somewhere?
classical. So exists multiple difference. So it's not fair to compare the logical circuits or the logical gates with the quantum gates. It's just not necessary. We can try to recreate, yes, but that is not the goal. Actually, consider with the caffeine, the molecule we can use working with this kind of characteristic in a variational quantum circuit and try to recreate it. And we don't need to do more like we can compute in a classical computer. We need to create a lot of time just to create it and a lot of bits because it's complexly like 10 to 48. But in the case of the quantum computing, for the properties, one molecule is property for one gate. Sorry, one qubit. So we're just using 160 logical qubits. So that's the difference. So we are not need to think in a classical way. It's more thinking in a quantum computing, and the idea of this one is not necessary to think arithmetic or video games, focus in that one. It's more try to solve problems where we thinking is complicated for the classical computing because it's not necessary to do another in a quantum computing if we're just to same 2 plus 2 or 2 by 2. It's more interesting try to recreate a way when we are trying to use multiple addition or multiple multiplication in an algorithm is necessary, yeah, probably the quantum computing could be better than consider a classical computing, but not just to do a basic operation. Even we can use a calculator for that one. So yeah, the interesting thing about the quantum computing is more like the short algorithms or Grover's algorithms. Had any question at this point? If not, I'll continue. Yeah, so the things about the quantum computing is like not just to identify the characteristics, just is recreate everything in the classical, try to say, yeah, quantum because quantum is better. Not necessary, it's more we can right now try to do the chemistry and the materials on like the optimization and search decision. So basically the things we are doing right now is like try to identify what is the problem we are getting in different topics like the aerospace, automotive, chemical, electronic and semiconductors, energy, finance service, and healthcare and life science, and thinking what is the possible kind of this problem and the use case and try to use a quantum computer. And the long term, we are will be more focused in machine learning or AI and numerical simulation. So right now we are trying to identify, for example, the portfolio optimization problem is a final decision for the service and do that one. Or the healthcare, identify the characteristic for a certain drugs discovery and try to optimize it or say it's valuable or no for the quantum computer, say the information. Or try to do a carbon sequestration or probably the aircraft computation fluid dynamics simulation of this one. So depends for this one, we create certain problems. A certain situation is complicated for a classical computing, and with a quantum computer, it's possible to do even if it's a complicated part for a classical computer, and try to see solve the use case and identify the quantum utility, like improve the results compared with the classical. So right now, the things we are doing in IBM Quantum is like using Qiskit plus the IBM QPUs and try to utilize the scaling work. So the thing is like we need to understand really well what is the codification, what is the programming part, the people who are in the background for the hardware, try to increase the fidelity of the information, identify what is the utility. So at this point is quantum must be performant, quantum must be easy to use. So the thing is like we need to identify how can deal in the hardware and try to recreate it. For this one, in having quantum platform, we have these different service and characteristics. Exists the Qiskit function for companies for the Qiskit Premium way. When other companies collaborated with our like partnerships, we have a specific function where try to recreate for try to solve a specific problems and try to do that one. And for our case, we had the Qiskit SDK, the Qiskit add-ons, and the Qiskit transpiler service. When we try to work all of this kind of information, try to optimize the circuit, try to recreate the circuit, try to identify the post-processing, and try to do the transpilation. Even with the Qiskit code assistant, improves the moment to program this part. And other ways we can do it is the Qiskit serverless and the Qiskit HPC integration, when we're trying to optimize in a every way for heterogeneous the characteristics of the hardware and the algorithms, and try to do even in a I think we are trying to do is the quantum computer. So it's like we right now try to use the CPUs, GPUs, or the AIUs, try to use with a quantum computer and see, well, we can try to do a preposition or post-processing using a classical computing. That is the things when we're doing in the classical part, and do the computational or the complex part using a quantum computing. And for that one, we need a Qiskit runtime. So right now we're focused with Qiskit using SDK. And interested or the goal of this one is just to work with the identify what is the circuit, what is the problem we are trying to do, try to utilize in a quantum circuit. That means is quantum gates and qubits. We need to recreate any problem on all of them. After that one, try to optimize the information for the target hardware we try to execute. And when we do the optimized circuit, we can move in a Qiskit runtime to just execute the information and try to do the post-processing of this information and see with the primitives, like could be the sampler or the estimator, is a good or a bad solution. So the things we're trying to do is using the Qiskit circuit library when we try to understand what is the problem and translate in terms of the circuits and the observables. The observables is the measurements, but what kind of the measurement we need to do. After that one is like, yeah, we have the quantum circuit, but what the tech backends, all the hardware working with a specific basis gate. So we can translate all this information of the circuits in a basis gate. So that means the circuits, yeah, it's nice. We can reduce in a simple number of the gates, but that not means is the gates understand the quantum, they are the backend. So the backends need to translate in the gates they know. That is the ISA circuits. After that one uses the primitives, estimator or sampler, identify is working or no. And finally do it this post-processing, so it's
Can
like
you just
we
make sure
can,
that your laptop is plugged in? It's about to die.
yeah. And the thing finally for the post-processing is just to visualize, connect, or try to identify in a simple way for like Instagram or expectation value way or in terms of the black sphere, the information we got it. So for this one, we're consider other properties we are getting like the multiple product formulas or MPF or the approximate quantum compilation or the AQC tensor for the Qiskit library, and for try to do for the transpilation we are consider operator backpropagation of the circuit current. And when we have to do after the visualization, we are try to working with the sample based quantum diagonalization or the SQD. So in terms of the quantum computing right now in IBM Quantum, we are trying to do is using all the function we are trying to do on the software like the Qiskit add-on and the Qiskit function implemented on Qiskit. Try to execute this one in the quantum hardware for IBM Quantum, and the goal is find a useful work. So basically, the IBM Quantum platform we try to do, all the goal is unlock research with quantum. So the thing I try to remark in this kind of last couple of minutes, just to remark is exists this hardware. Uh, we need to work with this hardware. So basically, it's like we working for this example for the upper plan. We are working with IBM Brisbane. We had 127 qubits, and the thing is like, we're working with the basis gates. This one, so everything any quantum circuit you try to do, we can reduce in terms of these gates. So we have certain noise, and we need to deal with this kind of noise. So this is a real connection for the hardware. So more black, blue color, I mean, it's really good. More purple, brilliant, or light violet color, that means more noisy. So you need to identify what is the connection is necessary or no when you try to understand the hardware. So I think I don't have time for my workshop, but basically the thing I used to visualize is you were interested during the summer school, I designed this laboratory, and this is solved. Just to remark in a general way is how can you working to create a specific problem using the noise for the real hardware. So in this case, we are trying to execute this problem for a noise model and try to identify, depends on the hardware, how can working with the noise, how can translate the noise, and we try to solve a specific problem. The problem is the math scout. This is a basic example for the quantum optimization problem where we design, well, we know what is the solution. This is the code for this specific problem, and the idea is to create this graph and try to solve it using a quantum computer, but we need to delimitate it with the noise. So the noise is part of the problem. So it's like I can translate this graph in an Ising model in terms of the Pauli operators and try to recreate in a quantum circuit we call it QAOA. It's a quantum approximate optimization algorithm. It's every way when you are doing a specific connection of the graph, recreate in terms of the rotation CC, and try to recreate it. We can work in this hardware, but the focus of this was is not understand the hardware or the algorithm or the quantum circuit is understand well. We're working on this one, but the consequence is the noise. This is good because the simulation, yeah, we got it in a generic simulation backend in terms of the step vector. But what happened? We are trying to do in a noise simulator, at least like try to recreate the noise for the hardware, so it's more complicated. So yeah, right now I try to recommend you if you are interested in check this one or you're part of the summer school, understand this one because the idea of the goal for this laboratory I designed with another couple of IBMers is like dealing with the hardware is part of the hardware or the noise is part of the algorithm we need try to do. So you take a screenshot of these links, or you are part of the summer school. It's just the lab two. Yeah, you're interested. Just take a look at this one. It's always right now. But I think it's important for if you try to understand more what is the quantum computer, what is the thing after apply your algorithm. So other things I want to take a look after more questions or interested about this one is like in avionics is different resource like the IBM Quantum Learning. When we try to create this kind of course, tutorials, and exercise, when you try to understand more about quantum computing, starting with a basic concept and try to do in a quantum machine learning, variational algorithm, chemistry, quantum deconvolution algorithms, and even try to understand the utility scales for the quantum computers.
Excuse me,
So I think
Alberto.
it's. Oh, sorry.
Can you please share the link to the chat so that we may use it?
Yeah, I can do it. Mm, mm, is there? Yeah, continue with this one. Yeah, it's this one. Yeah, it's this one. Yeah, the interesting thing about this one is other resources. You're interested more in a basic way or keep working in quantum computing, focus for IBM Quantum. This is a good platform you can start it. This is the platform. You just need to create your account. But yeah, practically quantum computing and practice is like the way you can start it. Other things we are doing in quantum computing is the community. A part of the IBM Quantum Learning is the Qiskit Advocate. When we are this community for advocates, you are feeling certain all of this course, you can obtain a specific badge and you attend certain background related with quantum computing. You have to be part of this community when you're even working in this quantum advocate or the Qiskit Advocate mentorship program when you're working with IBMers on another expert in the community and try to solve issues for research teams, educational, programming parts. Even we got at this Qiskit Global Summer School when we have these links when we're working in quantum computing. Exists the Qiskit YouTube channel when we work in these different techniques and properties about quantum computing, the new tools, the new techniques for people aspiring IBM how can understand more about this one and all the videos for the Qiskit Summer School you can find in the Qiskit YouTube channel. And we have this Qiskit Developer Certification for the new version for Qiskit version 2. So it's other good thing. Just to remark, in the Qiskit Global Summer School, we is 2 weeks for lectures when you can find in the Qiskit YouTube channel. The labs is in the same link I will share you. You will just go back in the general repository and you can find all the labs. And in this year, we had 8,000 people interested in this summer schools. So it's very interesting how the people increase in this kind of opportunities like this kind of event, like the Qiskit Fall Fest. And the idea is, yeah, try to do more activities. Like the Qiskit Fall Fest, we are create this kind of support events in person, online, or every way, just to do that one. So thank you so much to do this kind of events. because I think, and we think in IBM Quantum, and this kind of event is always necessary because, like we said, try to do more easy or accessible the resource about quantum computing. Qiskit is we need to use easy for all of you, and this kind of events, like summer school, Qiskit Fall Fest, is really important for us. So you're even interested in quantum summer internship programs in ABN. The application is right now open for across the world in different position in America, in Europe, in South Africa, I think so, and Asia. So you're interested in, well, what kind of roles, what kind of things, what kind of backgrounds you can need to use in hardware. It could be software developer skills, research skills, educational skills, hardware, and depends on the hardware, it could be other roles. So yeah, in Navi and Quantum, we're working in them. And yeah, we have the certification. We are starting with the version for Qiskit 02, what 0.2, and right now we're working with the version 2.x. So yeah, exists the certification where we are validated the skills to solve certain knowledges in Quantum and certain knowledges in Qiskit. So yeah, you're interested with the Qiskit Advocate program. We are working with more than 1,000 people from the community when we are doing this mentorship program, this kind of networking events, the events focused for advocates people, and yeah, you this kind of recognition in the community by you doing the advocates, and you get the opportunity to obtain the developer certification. So just to remember, the Qiskit Advocate program is kind of important because it doesn't matter the country you are there. Well, depends on the restriction we had in the platform in Avian Cloud. You can see that, but the goal of this one is like you are for any country instead of 10, you can make this general community participate in these networking events, do connection for other people around the world interested in quantum computing, like all of you, and try to do, yeah, connection, share resources, share opportunities, share different events, not necessarily the Qiskit Fall Fest, or even support for other people. And yeah, you are interested to do a Qiskit okay? I think this is
Yes.
the core.
Any questions before you proceed, yeah?
Yeah.
Okay. The first one is not a question though. I'm already a Qiskit advocate with IBM, so I'll definitely guide the people who are interested, right? And the next question, I think the only question now, you are previously showing the code where we have the control
Which one?
the control optimizer by linear approximation. Yeah, it was somewhere in your code.
Mm.
Somewhere within your code, I think slightly a little bit back still.
This one?
No. I mean, yeah, I think it was somewhere over there. The lab solution, there is the optimizer, where you have the control.
The control for this, or well, is in this notebook or in the slides?
Okay, can you maybe where you are doing the QML thing? Yeah.
Okay, I think is this one.
Yes, it was just within the code somewhere.
You remember the slide, the number of the slide?
Yeah,
Probably put it more.
just one of your codes. I kind of saw the control.
This one or what kind of song again? You tell me.
maybe we can keep the question for later, though. I can reach out personally.
Yeah, that could be better. Yeah, basically, I almost finished. Just to mention is like, yeah, you're interested in Qiskit okay, you are obtaining certain opportunities to do in this kind of seminars focused for Qiskit advocates. And depends on the activities you are going, you attain certain points, activities. In more activities, you attain more opportunity to convert in tier one, tier two, or tier three. And the best of these tiers, you had access for more minutes for hardware, or participate in more events, or participate for the mentorship program. So it's kind of related with this one. And yeah, basically that is my presentation. If you had now the slide or the part of the code you are interested or someone else had a question, I'm happy to answer. Mm, so you have more question or the guy who uh, asked me knows what is the slide for the code or anything?
All right, I
Mm,
think you are on the screen. Is the screen where you just clicked?
so it's in the slides or in the code?
In the code, like in the code.
Okay, here.
It just flashed and then disappeared. I don't know why it.
Which one? This one?
You know, Koibala, more like the optimizer. Mostly using the optimization problem, the cow and max cut problem. Yeah, so it just flashed on the screen and then disappeared again. So anyway,
So you're talking
yeah,
about
yeah,
this
yeah,
one, right?
yeah. Yeah,
This this one?
let me just. I've I've uh I've sent it in the chat right now. You keep on skipping that part of the code though.
Kobila is the classical optimizer, yeah.
Yeah, so now the question is okay, right there. Yeah. Now here comes the question. Do you consider that one of the best optimizers, or it's just good when you are doing the optimization problem like Kaoa and the max cut solutions here? Do you consider that it one of the best, or that depends on the kind of task that you're performing? Like we have the SGD, the Adams, etc. Yeah.
Depends on the problem. For this one, for this kind of problem, it's kind of simple. Yeah, Kobila could be a good one, but it's not necessarily could be the one. It's like, yeah, in the software, certain problems with of this one, but that not necessary to say the optimization is really part of this one. Probably the other problem is how to translate the cost function for the Hamiltonian. It could be the complicated part. It could be not necessarily using focusing QoA. Probably other ways just using more BQE. So the answer try to do just for a classical method for optimizer is not necessarily the problem. This is more depends on the nature of the problem, the goal try to do, and not necessarily QoA is just necessary for a complex problem. If you're doing more a complicated problem, QoA, well, we need more of the problem. The thing is like max cut is just beautiful for QoA because you don't need slack variables. But what happens you are certain linear constraints or multiple constraints? QoA, we need to work in a cube of problems. So cube is quantum yeah, it's like quadratic unconstrained binary optimization. So in mascot is not necessary, but what happened with all of this kind of problem is more real use case. It's more complicated. Try to use because translating is like variables increase the number of the qubits and complicated the Hamiltonian try to do that one. So Covilla it could be work, but yeah, that is not, to be honest, the problem when we are trying to use QAOA is other things. It's more translate the Hamiltonian, understand the problem. Probably QAOA is not the thing. It might be other ways. So yeah, for this problem, yeah, absolutely, Covilla is really good one.
All right, thank you. Is there any other question for Alberto? And also, Alberto, do you have something for us on 31st when you are closing the event, the Qiskit Fall Fest?
Well, yeah, absolutely. Yeah, in my case, yeah, I'm happy to be here because I think the Fall Fest is a good opportunity to share your knowledge, and not for me because that is the thing they pay me for this kind of activities. I try to do more for the people are interested to start in quantum computing. Is that you had the opportunity. Imagine for AI is no kind of simple to obtain a course for free or even organize and obtain this kind of support for companies. So yeah, I think it's a good moment. If you're interested in quantum computing, start to working now because in a near future, what happens after that one? Probably will be more specific or even you need to pay for that one. So in around the world, IBM try to help you to organize and it's not necessary try to do I cannot say pay for that one. It's for free. So yeah, take advantage of all of the resources we're doing for free for all of you. And you're interested in quantum computing, please go ahead and try to do that one. Because what happened in 10 years? We more it's like AI. All people are interested in AI. And when you get yeah, a job, it's more complicated. But you're starting right now, it's a good one. And yeah, the thing is like it's not necessary programming things using a quantum computer. Software developer people mitigate the error, understand the error, working with the compilation part, access multiple roles in different components. No, so you're not being interested in this one. So yeah, quantum computing is not just software and hardware. It's the general ways, but there exists multiple roles, multiple jobs in also this one, and even you need AI for working in there. So it's like, yeah, quantum computing is more a benefit at the moment you're working there. And yeah. I think you are mute, Brian.
Oh, there's another question there on the chart, and it's that's from Sheila Fana. She's asking, how is quantum computing currently being applied or explored in the field of robotics?
Well, it's not kind of important right now. The robotics are in quantum computing, but I know it's more for the control way. Exists a certain way like the fuzzy gates try to create it in that area in quantum computing, and the other is like try to recreate certain things using the geometry or the characteristics like the graphs in the robotics things. But right now is not. At least in avian is not an area interested for us right now.
All right, there's another question on the chart. I've noticed that Qiskit follows a clear build, run, analyze pattern when developing circuits, right? Are there recommended best practices for scaling these patterns for large algorithms or dynamic circuits?
Yeah, the thing is like the link I can send you is kind of taken to do this kind of good practice. Right now exists not necessarily for dynamics, but exists for optimization. We got it. Let me share the link here. Just scan it
Yeah,
for best practice for optimization.
I think with that also it points straight to more like the part that you want to cover. I don't know if you have time, the Vincenzo criteria, more like the scalability and being able to run more like algorithms on the same utility scale quantum hardware. So
Well, the thing is like we're explorers like this kind of practice. We got it. Like in this repository focus in quantum optimization is like try to use different preprocessing classical things and try to do this transpilation. So it's basically two steps. It's like you understand your hardware and try to reduce the unnecessary things and try to focus that with the hardware. So it's like the lab two, the link I showed you is like you have your hardware. So instead of this one is two things is or you focus your hardware or you focus in the problem you're trying to solve it, or both. So in a certain way, it's like where you're interested. So the best of this one is consider both cases because depends on the hardware you have certain connection in these gates. So that is one. The other thing is like if you are working with a graph for say something, they had a certain connection too. So it's like try to understand of this one. So yeah, basically is like the scalability is or the goal we are tracking doing experimental way is like yeah, you are working with small things and try to optimize in a simulation and try to execute during the hardware. That could be one. So it's multiple ways you can work in the moment using uses case, but basically it's just focus in the in the hardware, try to reduce the hardware, understand the compilation part, the transpilation, and the other thing is like read the state of the art. Not necessarily QA always trying to understand. Probably we need other techniques because, like I said before, QA with mascots is kind of simple because it's not slack variables. But what happens when you are working with more slack variables? The first thing is that is necessary. Six techniques we can reduce all of them because what happens if you had a problem with five variables with a slack parables, instead of just using 5 qubit is 23. What happened while working with 10? So it's 45, for say one example. So that is not a good way we can do the scalability because it's like, yeah, that is not necessary. But what happened is like try to reduce, try to understand, try to read. That is one problem. The machine learning techniques is like we are working with different feature maps, try to reduce it, try to try to recreate other things. It's not necessary to read the state of the art, understand the properties. So I think the things when you're working even with simulation or geometry is just not follow the idea like the bigger and try to recreate the similar like classical computing because that is the goal using a theoretical part. But you need to understand quantum computing has other properties. And yeah, that's the thing. You need to understand the quantum mechanics or the properties for the Hilbert state space and try to take a look because it's a complex universe. So it's try to take advantage of that one. But that case is take a lot of time to understand the properties of this one. So it's like collaborate, understand the things, or find a paper and understand that one and see, well, this idea is crazy. Probably we can try it, and it's good or it's bad. So yeah, it's everything is new.
there's another question there on the chat. That's from Ray Jones. I read about how quantum computers will be able to break any encryption algorithm that currently exists. If that is to happen, how is the field of cryptography and computer security brace? Hold on a second. If that, how is the field of cryptography and computer security braced itself for this event? Are there developments in new encryption algorithms that will be hard to be broken by quantum computers?
Well, the thing is like always exists this new like the security will lose when we get the quantum computing, but it's more because the short algorithms is try to solve the you can for a big prime number identify the coprimes for this one. That is the same characteristic you are working with the RSA, where it's part of the security we are using for all the work because it's a exponential complexity time. We are working with this kind of algorithms, and more if you are using a big number of the primes for the limitation of depends of the size of the computing, it's like 64 qubit, a 64 bigger prime number. So the thing of this one is, it's kind of simple because the RSA is solved in a polynomial time for short algorithms, but that is just the challenge for the encryption. But a quantum computing exists other properties. The more simplest way you can translate is, create other techniques. So Cisco probably they working in that. They working with the communication, and exists one techniques like BB84. When you are using one qubit, you can obtain a good security way. You can save your encryption key. So it's not necessarily that one. And in case it is a quantum computer, obviously we try to force the security. We are not like a TV series. Like we have a computer and we can obtain the money for all the work. Just even if you have it, it's like exponential time. It's like a polynomial time. Just next time to execute and understand one specific problem, but it could be not like in a seconds, probably a couple hours. Compare them with the security right now is a lot of years. So that is the difference. But the thing is like, it is certain communication, certain things. In IBM, we're not focused on this point right now in there, but other companies working in that one. And exists instead of they are focused in encryption, post quantum. Exists other ways we are just transfer the space of the information in another model using linear algebra. So exists that way. So so we secure the encryption is not die after a quantum tolerance quantum computing. Just is the interesting thing of the wall where thing is like when we got it, all of this one we need to change. That is the case. Will be changed many things. But
Do we have any question? Just feel free to ask. Let's wait for our next presenter about to join. They'll be joining in 10 or so minutes. Is there any question? Just feel free to ask. Alberto is here. And also Alberto, there are some people sharing screens, more like devices. So you are in a very, very big audience. Yes.
So actually the quantum device is kind of small compared when we're working. It's very small. It's kind of secure. Try to even touch it, but basically the architecture for the device is for the superconducting qubits. So the thing about that one is like, the old, well, probably you saw or even all the people in the news, this kind of fridge is kind of big. Let me check it. I think in the presentation I got it, this one. Uh, mm, no, I think I don't got it. No. Well, the basic things is like yeah, all of the systems, all these characteristics, just this is the device. So this is the device for the hardware. This is the quantum processor. Just all of this one is the fridge. We can try to put the quantum processor in a low temperature just to send information there. So yeah, it's kind of different. We are expecting a quantum computing, but yeah, basically the hardware is kind of small one too. Just try to use it this kind of big ones. So right now the quantum computing is more related in the system two. We're working in these kind of characteristics, and in IBM we're working and try to scale this fault tolerance quantum computing in the next couple of years, and using these kind of new systems for here in New York. So yeah, basically, if you are interested in quantum computing and try to work in this kind of area, is a good moment to try to start, because 5, 10 years we are more focused in more problems and try to solve more use case, and not necessarily in IBM or even in other companies, small ones, big ones, and yeah. So I think it's all for my side. Prior. So thank you so much for having me. I hope you like this presentation, and I hope you like to start working with Qiskit or IBM if you're interested in quantum computing using the IBM hardware and Qiskit. So thank you so much, everyone.
All right. Well, thank you so much for the nice presentation. And we'll talk so that we can have you over on 31st when we are closing the event. And thank you. I don't know if my co-hosts have something to say. Regan, do you have something to say? Shayla, do you have something to add? All right, so there are some materials that I will be sharing. They are provided by IBM Quantum, and maybe I should just take you through how to more like execute the problems. They're graded more like you will be sending back the notebooks if you attempt to. If you attempt them, then we'll definitely grade and give you a score. And I can promise you that if you get to score everything, we'll definitely end up with a swag this season, because this is a sponsored event. So expect swags if you complete the task. We have IBM assigned notebooks that you are required to attempt. So I'll just share my screen shortly so that I can walk you through how to run them, right? So can just give me a second. Share this. And of course, if someone joins when I'm presenting, then you can admit. I think I've delegated the rights to the co-host. So let me just share my screen right now. Should not be that though. It shouldn't be that. It shouldn't be that. Let me just minimize that so that it flies away. Right, this one here. Seems like I have several work. Yeah, let me just minimize them a bit. It's too much code done. All right, I think this is the final. Good. Can you guys confirm that you can see the screen? Perfect. Now, so we have some labs here that you are required to go through and attempt, and then you'll send them back to me so that they can get graded. Yeah, so you can import this code if you don't have an environment installed. Like right now I'm using IDE, VS Code. So if you don't have VS Code installed, you can install one, or if you don't like installing VS Code, then you can just go to the collab and import the notebook, right? And most of you are data scientists and software engineers here. So you definitely know how to import the notebooks. If you don't know how to, then you'll reach out to me and then I can help you. I'll always, if you access the website where you booked where you got the ticket, you can always find me. Just go to the virtual session link and I'll be there most of the time though. So can always drop me a text. So when you have your environment set, I'm executing this in the Qiskit type environment, more like it's a custom environment that I created. But if you import this on a Colab as a notebook, it will be much easier. You don't have to do prior setup. It will be very, very easy, and I'll walk you through if you reach out. Yep. So the first thing to do will be to more like install the dependencies here. And to install the dependencies, you just have to execute this, and it will also import the libraries that you require, right? But I see for my environment, this definitely won't run. So let me just isolate this. I can move this a little bit up. Let me execute this one right now. And this is going to be Qiskit visualization. Maybe it needs to be import. And I'll definitely flag this with a quiet flag so that I don't get the logs, right? So I'll execute this to install the dependencies that we require, that you need. Yeah, seems like I already have the dependencies installed. So that one already works out. Already installed this previously in the Qiskit environment. So when you run that, you'll see the log of everything printing, or if you kill, you pass in the flag for quiet, you won't see the the logs, right? So that one worked. So the next is just to import the libraries. Maybe you cannot here import the libraries. I'm going to show this one right now in the group. Import necessary libraries. So you run that, it will import the libraries, and from there, after importing the libraries, you'll start. You have to read through this. Maybe I can take you tomorrow, or when you reach out personally, I can take you through understanding how to execute this. So we have the qubit operators here, and you'll be writing your code. Yeah, you'll be writing your code right here, and when you execute, it should give you a result, and you'll save your work. Yep, and then send it back to me for grading. Yeah, I know you'll be working in the certificate for attendance from IBM, and also you will get an excellent certificate of excellence if you score everything here, and also get to work with the swag. I know that I'll have to pick that from the post office when they arrive, and then distribute according to effort that you guys will put, right? So we have this, and we also have the Vincenzo criteria here that's almost looks similar, but it has a different context. But I want you guys to go and read it first before we can go through them, right? So this is the next lab, and trust me, that the notebooks are easy to understand. Yeah, they're very, very easy to understand. So you can read through, but if you get stuck, you reach out, and I'll also set a time so that you can go through them in detail, right? I don't know if we have admitted our next speaker on the call. Let me just check. All right, let me just reach out so that they can join the call so that we carry on with the presentations. Today was meant to be a series of presentations. And I'm also going to share this in the group. So you reach out or you can text me. My WhatsApp number is on the booking page. I'll send you the notebooks. But if you get stuck, you just let me know. They should be easy. And you also have to do some reading. Yeah. Alan is not here. He should be taking us through the CH, the search inequality, the Bell states, but I don't know why I can't see him. Okay, so let me reach out to the next presenter so that they can join. Then we carry on, right? So you can WhatsApp me on that number. I'll share the materials directly to your WhatsApps. That is, if I have not shared it yet. So if you don't have the notebooks, you can just reach out via WhatsApp. I'll send them to you privately, all right? So Petra will be joining at exactly 5 p.m. Kenyan time. So we'll have to wait for her. And we also have 2 other speakers. Let me just confirm their attendance. I hope that's Braulio. Braulio, is that you? Braulio, are you the qubit first? Hi, is Braulio already on the call? Hi, Jim. Greg is already here, and Greg, can you just carry on?
Morning. Hey, good afternoon, Brian.
Good afternoon.
Give me a minute. I got to go do something. I'll be back in a minute.
Right, that's okay. That's okay.
Okay, I'm ready.
Yeah, we can hear and see you.
Good. Very good.
Yeah, sure. Good. All good.
I'm sorry. Say that again.
Your presentation is visible. I can confirm that.
Okay, good. All right. So I'm early, but you said it's okay to go ahead and start. Brian,
Yeah, I can hear you. I can hear you.
so go ahead and start my presentation.
All right, just carry on.
Okay. So we've all been warned about the dire this. So is that coming? Are you getting the full screen when I'm doing this? Is that guy's hat chopped off?
No, you're perfect. You're perfect. Properly
Okay,
aligned.
good. Okay, I hope so. I can't see. Anyway, we've been all warned about how Q day is going to be the end of essentially our lives and so on and so forth. Is that when Q day arrives and quantum computers are able to break encryption, that all of our privacy and all of our bank accounts and so on and so forth are going to be destroyed instantly. And that's going to happen soon, as in very possibly today. I hope I'm going to be able to share with you sufficient information that that's nonsense. And even when Q Day does arrive, it's still going to be many years before you and I personally are going to have any issues. So the estimated Q Day is going to be approximately in 2030, is what many of us are estimating, for the very simple reason that the timeline that IBM Quantinuum, IonQ, and two other quantum computer manufacturers are projecting for a fault tolerant computer is in 2030. There's approximately 80 quantum computer manufacturers in the world. I personally, professionally think that there's only going to be three that are going to be able to decrypt RSA 2048 by 2030. But let's make a conservative estimate and triple that number to 10. Additionally, it takes approximately 14 months to make a top-end quantum computer. Let's round that figure down to 1 year. So after 20, it's still going to take a year after 2030 is what I'm suggesting. And let's say that there will be 10 computers that will be built by then. McKinsey's also estimated the time to crack an encrypted bit of information with this type of computer will be almost 3 days. That's 3 days. That's a long time. Let's round this figure down to 2.5 days. And so even then, a single quantum computer is only going to be able to decrypt 146 encryptions per year per machine. And so let's stay with the figures that I've said so far. So in 2031, we'll have 146 decryptions times 10 computers. That's only going to be about 1,460 decryptions that will have occurred. For a typical computer use, meaning what you or I or any one of us do for typical usage, that's only the number of encryptions that we use in a quarter, in other words, 3 months. And so on our personal computer. And so you can see that these figures are very low. It's not like it's going to, the entire world, and most certainly our personal values of any sort, personal encryptions of any sort are going to be touched, because there's going to be many more, let's say, valuable encryptions that will be one that the bad actors are going to care to decrypt long before us, before they get to our personal information. In addition, McKinsey estimated it's going to cost about 64,000 US dollars to run a computer per encryption. So that's 9.3 million US dollars per decryption. So for all 10 computers, that's $93 million. And so this is the other thing that's been brought up by quite a few people, is who's going to be able to afford to do that? And so this obviously means essentially just nation states. And so it isn't going to be like hackers and bad actors are doing now, that anybody that wants to log on to the internet and start giving somebody else or try to attack someone else, they aren't going to be able to afford to do it. Another criteria is where are you when you're doing this?
Hi, Greg.
If
Just
you're in,
your
go ahead.
your slides are a little bit zoomed out.
That's what I was asking earlier. So you're not able to see all of them. Hold on.
Can you do command and minus? Yeah, I think that one is now decent. Yeah.
Well, that's what I was getting at. So I'll just have to do it this way. And so this is what I was getting at, is you weren't able to see that entire picture the first time then, were you? Brian?
Yeah. That's not okay. That's not okay.
Yeah, that's what I'm getting at is when I go to present the slideshow, it evidently cuts it out. So I'll just have to do it from inside here. Let me,
Yeah, it's visible. Can just increase that. Yeah.
there we go. Better. And so you weren't able to see the other ones either then. So this is what I said earlier, and here's the text to go along with it. Ditto with the time to run. And then the cost to run. And so can you see, you can see all that now, can't you?
Yeah, sure. That's now visible.
Good. Okay, good. And so yet a third constraint, we've got number of computers, a fourth constraint actually, is we've got number of computers, we've got time to run, we've got cost to run, and the fourth one is political. If the computer is in an authoritarian country, the computer or the at least the use of it is going to be just confiscated. What I envision happening, at least in the United States, is that the government is going to force whatever manufacturer, let's just say it's IBM, into a mandatory contract, and that the US government would then get exclusive use of that computer for however long they dictate. And they can put a lot of stipulations on that, or would put a lot of stipulations on that, in that saying things like, or restricting IBM from saying that they've developed a computer that is now Q-Day capable, permitting any press releases on their achievement or anything else. And so this is what I claim will be the fourth criteria. And so these days of the statements about any of us having to worry about any of our private information are is actually quite complex. We've got to satiate all four of these parameters before that could happen. And so the groups, and so let's say that does happen. I'm claiming that the only groups, at least for the first year or two, that are going to have to be concerned at all are departments of defense. Obviously, when one gets into defense matters and keeping one's country going and sovereign and so on and so forth, expenses are immaterial. Expenses are no longer a criteria. The departments of Treasury, for obvious reasons, but it's departments of Treasury at nation state level, because obviously many countries have hundreds of billions and trillions of dollars in the Treasury. And so people like you and me, even if one is a billionaire like Brian or someone else that has that much money, you're still not going to be of interest. It is one needs to have a lot of money before you're ever going to even be considered. And central banks are obviously in that category as well. Somewhat secondary, but still possibly of interest, is that personal medical records. And this would be of limited number of people, like say the leader of Kenya or the leader of any state, leader, the president of the United States, and so on. And the reason for that is because once one would acquire their personal medical records, they could then start to use that to bribe or do extortion of some sort, is what I claim. And eventually, of course, those records could be decrypted, but at least initially, I don't think it would be worth someone's time to do it, but that's of very of secondary or like a 1.5, and not necessarily all the way to a second level, but these are the groups that are at interest or that would have the greatest liability. So where does this leave us? To keep working on our encryption, our PQC, post-quantum cryptography, as we've been told to do presently, especially to work on the store now, harvest later, the store now, decrypt later, excuse me, harvest now, decrypt later, as it's oftentimes called. But my point with all of this is that the fear and the anxiety that all of these naysayers, these people that don't know anything about technology, are claiming is fictitious. I hope that I've been able to express with you, share with you that all four of these criteria have to be met before any one of us or any institution needs to be concerned about having any of their privacy matters decrypted. So with that, I'll just leave you with the last word, something somewhat humorous, and then I'm open to any questions that any of you might have.
Anyone with a question? Seems like there's no question. You can just carry on.
Well, that's it. That's all I have.
All right. So maybe we can wait longer if someone has a question.
Sure. Oh, so Qubits Force, I didn't see your chat note. I wish I did earlier. I would have changed things earlier. Anyway, all right.
No worries. Just a general question. Do you believe that this work that we're doing at the post-quantum algorithms is then necessary to do?
Yes.
People
For
in
the
the NASA or US security forces are saying you need to have a post-encrypted but classical quantum algorithms that, are different, aren't they?
Yes, the NIST standards still should be applied as expediently as one can. There is a one group of two individuals who are pointing out that there are quite a few websites that are already implementing many of those, and the browsers, especially Firefox, and I'll go into that in a minute, is that everybody should absolutely be running Firefox and not any of the other browsers. Is that most of those NIST standards are already being implemented, most certainly on the more commonly used websites, in other words, like Yahoo, Google, and so on. The reason you want to do that is implement those standards is because of the store now, decrypt later. Oftentimes, what I don't like the wording of harvest now, decrypt later, because you aren't harvesting it first. You're just storing it. Harvesting to me means that you're doing some work on it immediately, and you're not. You're just storing it. In any case, with that store now and decrypt later brings up yet another criteria. Hold on. That And so this brings up yet another criteria. If you are one of those in one of those four groups, let's say, especially our personal health information, that definitely needs to be hidden or encrypted in a manner that's secure that quantum computers couldn't decrypt. But let's say it's something like a bank account or your login to your email account is just because of the software and hardware changes that go on, the typical lifetime of those type of values usually is only a couple of years. And so with, let's say it's 2030 and you've got whatever, the usual too many things to do as we all do. And I'm claiming I wouldn't, at a personal level, I wouldn't be too concerned about encrypting or doing much about your bank account or your log into your email because within 5 years, the values that you're using are almost certainly going to be changed by then. And so it's not going to be of interest. And so what values they have stored presently are no longer going to be valid and they aren't going to be able to get in anyway. Does that answer your question?
It does, and it makes sense. Yeah. Thank you, Greg.
Sure. Thank you. Thank you for your question.
The next question. Still open for questions. Anyone?
Sorry, just a follow on mine. Greg, you mentioned Firefox. Why did you say Firefox?
Oh, good. Thank you. I'm sorry. I meant to bring that up. The reason for this is because those two gentlemen website, they showed that it was following the encryption. It was staying more advanced, staying more current with the latest PQC standards than Chrome and the Microsoft product. The more so is, and I don't use the Microsoft product, so I can't speak with it. The other thing that I found is Chrome has a problem with memory leakage between tabs. Firefox does not. And by that, and you can test this for yourself, is that if you open, let's say 10 or more tabs, I find that the speed degradations that I get on Chrome, and maybe it's only on specific websites, specifically Google Voice and Google Calendar. But in any case, I find that the speed degradation that I get with Chrome is considerable. But if I do the exact same thing on Firefox, I can have 1,000+ tabs open and it never slows down. So implicit in that is if there are memory leakage problems of some sort, it's just a matter of time before someone's able to find it. But bigger problem, the media problem is you're able to use it. It slows the browser down so much it becomes very frustrating, to put it politely, to be able to use Chrome or the Microsoft product by comparison. And the reason I'm saying all the rest of them pretty much because all the rest of them use the same underlying architecture and code that Chrome uses, while Firefox has its own. And as history has proven to us, Microsoft has never been trustworthy as far as encryption or keeping things secure, and Firefox always has from the very beginning, which is when I was working there as a developer. That was always a criteria. Before we put down the next line of code, it was okay. Here's one of the parameters it needs to satiate is does it violate security problems? And from what I'm seeing, I obviously no longer work there, but what I'm getting at is that by the way the browser acts and reacts to things that we're doing, it still appears that that criteria for coding, for programming, is still very much in place.
Yeah, great. I'd seen things like DuckDuckGo browsers like that, and I wondered if they're better.
Right, exactly.
Thank you.
Sure, thank you for your questions.
All right. Just a quick question. Do you see the Q day happening before 2030, really, according to the current technology advancement that we have?
So someone thinks that it's going to happen before 2030? Brian, I didn't understand the question. Would you say it again slowly?
I'm saying, do you see the Q day happening before 2030?
The earliest I see it is 2029. And the reason for that is look at the new timelines, that the release maps that IBM, Quantinuum, and so on have had. All of them are saying 2030 for their fault-tolerant computers, which is what you're going to have because the number of calculations that one has to do to be able to run the Shor's algorithm, to be able to decrypt the encryption is into the millions of values, and until you have a fault tolerant computer, you're not going to be able to do it. I claim even if someone, and I believe IonQ would be the only one that might be able to do this, even developed a computer in 2029. Again, look at the other values that I shared, that it's going to take a year to be able to make a production machine to be able to do this. Even if they hired a lot of people to put it together quickly, I mean, let's say they had developed it in the middle of 2029, it's still going to take them at least 6 months to put together. I mean, we've all seen, or well, maybe you haven't, but you've seen the photos of being in a lab and all the parts of the computer are spread out all over. And that's for a very good reason, is because you want to be able to change and move things around so you can test every little bit of it. That's the reason you have the lab to begin with. To do that for production is nuts because you're not going to be able to reproduce what you've done previously. And so the entire construction of the machine needs to be done differently in a way as the computer in front of you now. It's a solid piece that is in one, it can only be configured one way. So there's reproducibility.
All right. Now, assuming we achieve 100% error correction this year, and maybe scale the qubits to 1 million, do you think the Q day will come sooner?
You get into a gray area when you ask that. And so there but presently the RSA 2048 could be decrypted, but with a few of the machines now that only have about 1,000 qubits logic, and so those would be logical qubits because they need to be fault tolerant. But the problem is that when one is attempting to decrypt that encrypted bit of information, it then takes literally weeks. And so it's a sliding scale. And so if you've got more logical qubits, then your time decreases. But if you have fewer, like we do now, then this goes up substantially. And so to answer your question is that the medium ground is what I'm describing as 2030. And that almost certainly is going to be the quickest it's going to happen. And so it's still the same thing. I mean, I've allowed for that in my comments. So did Mackenzie with those values that they shared, is that the quickest we think, most of us think that it's going to happen is going to be around 2030. And I described what might happen if it's 2029. It still is not going to matter that much because you still have to develop, you have to construct a production machine that can sit there and work for essentially the full year to even get you just a few decryptions.
So do you see some quantum cryptography algorithms being developed in time to encounter such threats? Yeah.
I'm sorry, would you ask that question again?
Do you see some algorithms and cryptographies that will be developed between 2030 to counter such threat, like the threats that the Q-Day bears? Yeah.
So to counteract it or to make it happen more quickly?
To counteract it.
Well, isn't that just the NIST standards? And there's other ones, but I mean, the NIST standards directly try to address this, don't they?
Yeah, they do, but don't you think they are? We still have a lot to do to more like achieve the certainty of not being hit by the Q-Day, though. Like,
there are algorithms being developed all the time, obviously, and one that has helped with a speed increase for many types of computers is the low density parity check, the LDPQ, that you might have seen the acronym around. And that most certainly is giving a speed increase in processing power. But again, there's quite a bit of leeway in the estimates that allows for that. And so again, I don't see it happening any sooner now.
all right, Tom Lee's hand was Tom Lee. You raised your hand. You have something to say?
Hello, can you hear me?
Yes.
Loud and clear.
So my question is that I've heard so much about quantum computers, but I've been wondering, how do quantum computers store like information that they process, and is this going to affect the
Wait,
noble
Tom Lee, would you get
Yes.
closer to the mic? You're so soft, I can't hardly hear you.
Okay. Can you hear me well now?
That's better. That's much better now.
Yes. My question is that I've heard quite a lot about quantum computers, and I've been wondering, how does quantum computers store their memory, and is this going to affect the traditional way of storing memories? Because mostly we use servers, even though we use servers to serve our data, but the servers also act as a point of storage for our memories. And if all these things are going to be affected, how is it also going to affect our field for programming? Like, I'm a developer, and I know there's a programming language already made there. If I'm not wrong, I've heard about qubits things. How is it going to affect our field in the programming? Are we going to like restructure our way of understanding how things work and program in a different way? And the information storage, are they also going to be stored in a different kind of manner? Are the compression techniques going to change? Because for us to reach at this point, there are several things that have been invented, like compression techniques to make to store quite a lot of data, but using a little space. So are all these metrics going to change, or quantum computer is just going to work hand in hand with the already existing technologies?
Are you familiar with the 7-layer model?
Not really.
Okay, please look that up. In that there are 7 layers in the way that a computer hardware and software work. And you're asking questions many layers below what, well, at different layers than what the software would work for you and me as a programmer. And so they, those questions about memory and so on and so forth are on a complete different layer that we don't influence or affect directly when we program. And so it will all be handled by how the computer is configured, and there will be no change as far as what we do, how it address the memory. The memory will be stored in a different kind of unit. It'll be stored in a qubit. But again, that isn't something that at the layers that we're talking about that we deal with, the upper 3 layers that we will ever see or ever touch.
Uh, I just wanted to repeat because you've spoken about the 7-layer model. If the 7-layer model that you're speaking about, let me just, the one that is the application, presentation, session, transport, network, data link, and physical. The networking, the OSI layer model is the one that you're referring to. Is that true?
Correct. Correct.
So you've said that quantum computing will want to be affecting which layers. From which layer will you be like starting the effect from?
I'm sorry, which layer what?
Oh, you said that there's layers that quantum computing want to be affecting. Is that right?
We won't be interfacing with it directly. It will be addressed just as it is now, is that when you program now, do you deal with those matters? And so my response, my to your question is that it won't change anything that we're doing now because it will be on a layer so much lower or different than what we as programmers, as users, interact with, that we still won't see it. We still won't be dealing with it.
So I know you have information about programming. There are some programming languages that something like Rust, where memory is being conserved. You're programming based on memory that a system has. So such programming languages, they usually go deal with the core system of a machine for it to save more memory. But then quantum computing will be acting in a different way. It will be like uh, uh, binary. Quantum computing don't deal with binary, and most of our programming languages they're made in the concepts of binary kind of programming. So is there a way will quantum computing for it to like integrate with our normal day-to-day life? Is is it made in a way for it to process the binary form, or everything will be have to be changed to go into the quantum computing way?
So you're talking about programming in something like, to me, it sounds like from what little bit I can hear, because I'm sorry, I still can't hear your half the words you're saying, is that you're trying, it sounds like you're attempting to program an assembly. And assembly is available on quantum computers, but even then, on any machine, when you program an assembly, it still is compiled. And so again, that's still going to be at least a layer or two away from what you or I do as a human. So once again, it's not we as developers, we as programmers, most certainly any end user will not see a difference. As programmers, yes, we'll see a difference in that we'll have to program in a different language, but the concepts are still exactly the same.
And also,
Good. I'm glad.
also on top of that, when you do quantum simulation, and the only thing that you most likely will be doing is just accelerating the computation. Otherwise, there's the part where you do the measurement, and when you do the measurement, the quantum state collapses to more like a classical state, a definite state that you're used to.
Correct.
Yeah.
Correct. And then the other thing too to remember also is that all quantum computers at this point have a classical are the best way to think of a quantum computer presently is think of a mainframe. Mainframe computers have preprocessors and postprocessors. That's exactly what present day quantum computers have. The data needs to be placed in a certain form, a much different form than what classical computers do. And so to get it into that state, a preprocessor that needs to be run to enable that to happen so that the quantum computer can understand it. And then when it is output, that data needs to be put into a format that we as humans can understand. And so think of a quantum computer again as a mainframe, and instead of having a classical processor in doing all the work in the center part, they're doing the heavy calculations, it will be a quantum computer doing those calculations instead. And so the thing that will change, that I keep hoping that the companies developing sensors, quantum sense, when one does input through a quantum sensor, the pre-processing doesn't need to be done because the values, that the data is already in the quantum type protocol, the quantum type of code. And so this having to encode the data is actually one of the bottlenecks of using quantum computers presently. And that is one aspect of what quantum computer development, that's one area that some people are working on because it slows things down a bit. Any more questions?
Oh, I have one question. Do you see a foreseeable future where people will be able to like have quantum computers like the laptops? For us, we have the laptops. Computers started from the mainframe computers. Just bulky, no one could access it. Will quantum computer also reach to the point where we use them like laptops? And what is your, like, after how long, if it's possible, how long will it take to reach at a point where it's the size of a computer or a mobile phone?
at least a decade. At least a decade. For one, the very first part of that is that most technologies of quantum computing are requiring extremely cold temperatures. And so just to have that apparatus alone, those technologies that are using that are requiring the extremely cold temperatures will never be able to be converted to a laptop. And so again, the question is similar, at least at this point and at this level, to be able to have a mainframe as a laptop. It's not physically possible. And so the other way I like to describe quantum computers are how one accesses a mainframe is that you still go through your laptop or your personal computer, whatever type it might be, but then you go up onto the cloud, onto the internet in some way, and you utilize that quantum computer or mainframe. Once again, analogy to a mainframe is perfectly applicable, is that is how you access it presently, and that is what's going to be happening for an extended period of time. So that would be my answer to your question.
We can take 2 more questions. If you guys have 2 more questions, you can bring them.
Hello, Brian. Can I ask a question?
Yeah, sure. Go ahead.
Okay. Will there be new jobs when quantum computing breaks out and becomes the norm?
Whenever a new technology is introduced, there's always a shift in jobs. Some of the older jobs will be lost or at least changed, but there will be new ones introduced. So the quick answer is yes, there will be new types of jobs introduced.
Okay.
Yeah, for example, you say we have quantum machine learning engineers. We'll have that. We'll have people who will be doing simulation for quantum chemistry, people in research, people handling the hardware itself, like a lot of jobs out there. So there are definitely, even the quantum outreach, quantum econophysics, there are just several jobs within the quantum domain that you can apply for, or maybe you can purpose to learn, yeah, so that you can get a job in such.
To me, though, as far as quantum is concerned, it isn't really, in a general sense, it isn't that there are new jobs. It's just that the jobs are different. The programming you're still gonna have programmers. It's just that you're programming differently. The hardware that you're dealing with is different, and so you're still gonna have computer engineers and computer technicians that are assembling the computers, but it's a complete different type of hardware that one is assembling. And so to me, the question isn't that there will be new jobs, it's just that the old jobs will be changing a bit to allow for and do what is required for quantum computers.
Yeah, sure. And also say for the people who are doing quantum research, I mean, we have
yes,
yeah, we have more like the people doing the error correction. Yes, Those are more like just new jobs, but yeah. So do we have any more questions that we can take? Petra will be joining us in 16 minutes, so we still have a lot of time. We can discuss just random things, not things limited to the Q day though. Yeah, so if you have questions, you can just ask. Yeah, the kind of quantum computing or quantum questions that have been bugging you all along, you can bring them along. Perhaps you'll get concise and informative answers, right?
So hello, once again. I know it's hard to hear me, but I have another question. Um, the story about quantum computing has been there since quite a long time. People have been talking about switching to know more about quantum computer. It's going to take over the world and everything. But then for us, example for me, I'm in Kenya, but we don't really know the rate at which quantum computing is spreading to the world. Before new technologies are actually adopted into the world, the perceptions of engineers is not always correct based on what I've seen. It just depends on how people adopt it into the daily day-to-day community. So is it do you advise someone to start getting into quantum computing as early as now? Is it something that you see the world adopting it in a good rate or with a good attitude? This is something that people could change into as an advice for someone who is working with quantum computing and trying to sell it to the rest of the world.
I'd like to slightly change your question a bit, if you don't mind. This is the second wave of quantum technology. The first wave was lasers, and so anything that we use as a laser, from anywhere from a pointer to a CD player to Blu-ray to any of those devices and any of those technologies, all of those are part of the first wave. The other part are devices such as MRI, magnetic resonance interferometers that are used in healthcare. All that was part of the first wave. We're presently in the second wave with what's starting to come on, especially with the scientific explorations that Brian has described, molecular simulation and so on, and pharmacological development of drugs and so on and so forth, as well as what we've explicitly been discussing here with quantum computers. There will be many of us strongly feel that there will be a third wave. And that is because when we hopefully can get out of just doing probability and start to make and start to be able to determine that when a value is given to us by a quantum computer, it is precise and reproducible exactly out to a million different, a million, or whatever, an extremely long number of zeros to the right of the decimal point, is that it's reproducible every time. When that starts to happen, that will be the third wave, and that is when radical changes are really going to start to develop in what quantum computers will bring to our societies, our cultures. Does that, I didn't answer your question directly, but is that close enough? Does that answer what you're looking for?
Yes, 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 it does.
Yeah, okay, the next question, as we wait for Petra, we have about 12 more minutes to go. Moses, you haven't spoken. Do you want to say something? Asman, Lois, the quantum questions that you have? Whether it's concepts in quantum mechanics, not necessarily limited to quantum computing. Yes, Ray?
I had a question on. Okay, Greg has said that the quantum computers need a certain temperature in order for them to work. So does this mean quantum computers won't be commercially produced to be used at, let's say, homes?
Those types of computers, those type of quantum computers that are using those technologies, which is most of them, correct, would not be used in a home. They would be, first of all, it'd be too expensive. Well, that or second, the other part of it is that it needs a lot of apparatus to support it. The dilution refrigeration equipment is oftentimes as big or bigger than the actual computer itself. So for those two reasons alone, with those technologies, that's correct, that it would not be used in a home. When if there that that with photonic technologies, the temperatures being taken down to almost absolute zero aren't required. Those aren't forecast to be developed as quickly. And so it might take yet another year or two or three before those even become commercially available at any size, in any room, anywhere on the planet. The other technology that is doing that is that one technology is to use existing constructs such as silicon, and that also runs at room temperature. Again, it's quite a bit slower than the technologies that require near absolute zero temperatures to be able to operate. But again, those run much slower, and so the output, the values that we would be deriving from them would take a lot longer. And so for them to stay for what this for what I was discussing about Q-Day, those technologies to be able to accomplish the same thing would take a lot longer, maybe orders of magnitude, probably orders of magnitude longer to be able to process.
Yes, Chamle Karian.
So this one major challenge that quantum computers use, that is the cooling. You say that a percentage the quantum computing itself is quite small, if I'm not wrong. So at this stage, there's a lot of people investing in satellites, and there's like Starlink has a lot of satellites in this at space, and one of the properties there at space is that space is quite cool. Like in movies, I've well confirmed it, but in movies I see people when they're out in space they freeze. So is this something that you, as people who make the quantum computers, have thought of, like having quantum computer and deploying them in space and having the process all this?
Brian, could you tell me? I can't hear Tom Lee. I literally
More
had
like
at least three-fourths. So just ask this question to me, would you please?
more like the space is already cold. Do you think quantum computers can be built just to run in the space? That is more like to account for the temperature changes. Like you see more like um the qubits require sub-zero temperatures to function optimally. Our scientists thought of more like building quantum computers in the space.
Oh, in outer space?
Yeah, because the
Okay.
temperatures.
Yes. Yeah, no. It's a fair question. The problem is that the quantum computers presently are operating at temperatures 100 to 1,000 times colder than outer space. Colder than outer space. And so even though that helps, and it would be easier, nicer, cost less, more efficient to do it in outer space, that the temperature in outer space isn't cold enough. And so recently, a company was able, or excuse me, a research firm was able to develop a the superconductor. The temperature was able to be raised all the way up to like 1.1 degrees Kelvin instead of being minus, or, I mean, a hundredth or a thousandth of a degree Kelvin. And so the amount of energy that it would require would be obviously a lot less. But even now, one or 2 degrees Kelvin, excuse me, 1 degree or about 1 degree Kelvin, it's still colder than outer space. Outer space is approximately 6 or 7 degrees Kelvin. And so, see what I'm getting at is that it is so much, the work that is being done with quantum computers at these super cold temperatures is again colder than outer space.
And maybe yet another interesting question, right? Do you think that at a point people will invent more like atoms that can more like do the same thing, the same work the qubit does at more like a room temperature, so that we don't have to worry about cooling?
I'm sorry. The one of the most important words or two in the middle of what you said dropped out. So could you ask the question again, please?
Okay. Like you say, quantum computers can help you to more like discover new particles, right? Do you think at a point we'll discover a particle that can more like act as a trapped ion, but they run or simulate stuff
At a
within
higher
the.
temperature, at a higher temperature, that would be wonderful if the quantum computer could find its own solution. Yeah, but I have no idea.
Yeah, maybe we are just looking too far. Yeah, maybe we just not looking at the correct place to. Yeah.
Agreed. It would be wonderful if quantum computers could find its own solution. Sure.
All right, maybe we can have a final question
And
and then we wrap it up.
one more question.
We lost you. Can you come up again? We lost you.
So I I thought that when at higher temperature,
Won't hear you. Can you type the question? Is it my connection now or it's his?
His. Yours is fine. Yours hasn't changed. Tommy, you're confusing things. Is that is part of the problem, is because the particles are running quicker at higher temperatures. We're not able to control them, and that is the problem, is that they need to be slowed down to a point where we measly humans can do something with them. And so that is the reason they need to be cooled, super cooled.
Is there any more questions? Anyone? Anyone has a question?
Greg, it's me again. Just a quick question of the technologies you've seen for quantum computers, cold atoms and annealing and things. Which one do you think is the favorite runner at the moment?
There's at least three technologies that are all top contenders. IBM's obviously superconducting. There's neutral atoms. There's trapped ions. I would say one of those three would be the top contenders, but that's my crystal ball. To go that part down, I mean, I'm throwing darts. I have no idea.
It's interesting that in this particular technologies, we're still open on the potential technologies that can come on. Yeah, not they haven't yet, which is a good thing,
Yeah,
I think.
it is. But one of the one area though that one technology will be the only one used is when we get into networking. When we start talking about networking, photonics is the only thing that will be used for the very simple reason that it doesn't require any cooling, any supercooling. And
Yeah.
so everyone is, I don't know of anyone that's even thought of doing any technology otherwise for that simple reason.
And it utilizes the fibers and that are in place, right? So, and then you can
Already
do
in existence.
quantum
Yes,
and
that are already in existence. Yeah, yes, correct.
But there's no, I know you the cryogenic atmospheres, but you don't have any silicon-based quantum computer technology, right? With
There
for
is.
oh,
There
is
is
it?
actually. There is. And that I mentioned that a little bit earlier, and it was just briefly. That was the other one that I said that doesn't require cryogenic temperatures. It it they use, and one of the main, well, very substantial, huge advantages of using it is that they can use present silicon technologies, silicon foundries, and so on and so forth.
Yeah.
And so the cost of it, and just as you were mentioning with using fiber optics and so on for networks, the same type of thing applies with using silicon to do the calculations also. But as I mentioned, well, you didn't hear that part. So the problem is that there's a speed degradation, and it's not just, one or two times. We're talking orders of magnitude slower when you go into photonics and silicon versus the cryogenic temperatures, at least at this point.
Got it. Yeah.
Thank you so much, everyone. And I think that has been a long, nearly an hour QA session, right? So thank you, Greg, for the nice presentation. And our next guest speaker is here, Petra. Welcome, Petra. Maybe you can carry on.
Thank you, everyone.
Thank you. Hello. Hi, everybody. Really happy to be here with you. I was just wondering what the setup is. So this is organized by, I think, the University of Nairobi, right? And then also the Quantum Fusion also that is working on it in Kenya.
Nairobi Quantum Fusion.
Yeah, okay, all right. So really thank you to be here. I am Petra Florizone, and I am responsible for quantum at the global level, but more focusing on building partnerships, creating the ecosystems. So I just heard the last one or two phrases of Greg and Qubits Force. So I am not technical, so I am really more focusing on how to help them, people starting. And although I am part of IBM Research, I'm the link between IBM Research and the business side, or what can we do with it? What can we do with quantum? So that's a little bit more the idea. I can share my presentation. Is it the goal, Brian, to present here?
Yeah, sure. Carry on. Carry on.
We are? Yeah. Okay. just to align to what is expected. Let me see, because I'm not used to use Zoom. That's why I was also a little bit late. Let me see where we are. Yeah. Share.
It wasn't just you, Petra. It wouldn't let me in.
Oh, okay. Let me see if this works. What is this?
That definitely works.
To bypass the system. Okay, we'll see. Let me put it a little bit bigger. So, yeah. So I'm responsible for, I'm working at IBM. I think everybody knows IBM, and I hear a lot of specialists here in the room, in the virtual room. So I think it's good to know all the perspectives, and you know that we all have different technologies out there, and we are focusing on superconducting. But not only that, we don't want to do technology for technology, and we really want to do something useful for it. So our goal is also looking at what can we now do with this technology at the application level. So that's our main goal. And you need to, excuse me for 1 minute, sorry for that. I'm so sorry for that. But on the other hand, we also have quantum safe. We all know that there was a lot of things to do around quantum and the protection and the security, and we also know that there are always some bad actors if you have emerging technology. So we also focused on quantum safe at the IBM part. We all know what quantum is, so I'm not going into that, but we all know also that quantum will certainly not replace classic computing. That's certainly not the goal. So we will see where do we see the use cases, where do we see the domains where quantum can be interesting. I think you all know 3 main domains: simulating nature, molecules. Simulation of molecules is, of course, always a challenge with classic computing, but also machine learning and optimization. And like I said, lots of things can already be done. What can we do more with quantum computing? And there will still be things that we will not be able to do even with quantum computing. We are working a lot with industries as well on specific use cases, and here I will just highlight a few of them. Thinking about if we talk about molecules, simulation nature, and what can we do? What can we get out of it if we use quantum? Is it more accurate results? So we have been working for a long time in the automotive sector. Think about Mercedes, where we work on the battery technology. We already have, of course, batteries and the electronic vehicles, but we also see that it's not optimal. There's certainly room for improvement. So that's certainly something where we are looking at. We're also working with Boeing, for instance, on materials. One of the biggest costs for airplanes is erosion. So can we look at what is erosion doing? What is the chemistry doing? And can we improve that? Or can we define new materials where we don't have these high erosion costs? I think we also know that looking at new drugs discovery, how can we do this much faster so that we can also bring the new drugs faster on the market, which of course is good for the whole society. And then we are working with, and there we work with many companies, but one of the ones that is really very much focused on it is Cleveland Clinic. So they are working since years now on drugs discovery. And then we have another example is MRI. We work with Moderna on MRI and how we can improve that one. So there we also see some first good results. That this is more on the accuracy that where we are looking at improvements, but also looking at other spaces. So finding the hidden patterns like anomaly detection. That's something where we are also working on. This can be in different areas. It can even be with cities, for cities or big events, but also in the financial sector. Think about fraud detection. If you could have 1 or 2% of improvement because in fraud detection you have a lot of false positives. If you could have already some improvement there, that could be a lot of savings for a bank, because all these false positives, it also means that a person needs to look into it. Is it false or not? Is it real fraud or not? And that could mean if you could improve there, that could also mean a good saving. Cell therapeutics as well. So also very targeted medicines it's also very important. And then if we look at the financial sector, we also see a lot of risk assessments or optimizations, where we see also, of course, a lot of results. Think about what we are doing. We just announced something interesting with HSBC. HSBC, they are working also on trading algorithms. And there they came, was it last week or the week before, they came with 34% of more an improvement, 34% of improvement in trade fill product predictions. So that means billions for them. So it's not in production yet. Of course, we're still in research within Quantum, but these are really good first results that we see. Also Vanguard, also a large bank, where they are looking at portfolio optimization. We can already do a lot of optimization with classic computing, but we simplify the variables, or we decrease and we make sure that it's not the immense amount. And also there, Vanguard published some good papers there and good results. We also work with Mutual, so lots of large banks that are really looking into quantum computing. And then if we look at optimization, of course, vehicle routing, another example. I just like to give examples to make it also more concrete, that it's not just a dream what we are doing. But for routing optimization, we are working a lot with ExxonMobil, for instance, for their ships. So optimization of the routing of their ships, because they need to transport their gas. So that's also one where we are working on. But of course, vehicle routing is it's for automotive, it's for airplanes, it's for ships. It's all transportation focused. Of course, it's really good. We're also working on, for instance, what are we doing also with E.ON? E.ON is electricity. Grid optimization, for instance, is also one we are working on. And these are just a few examples, but we see, of course, many use cases. And I think if you're working on quantum, that you know most of them. And there were so many that we still don't know. So that's why we are always trying to focus also on building this ecosystem and growing the ecosystem, where we are inviting partners to work on algorithms. So I think that's our main goal. Because what are we with our systems if nobody would use them? So the goal is that people focus on the application part. And yeah, you can see that across the industries, we see lots of interest. And sometimes we see, like E.ON, they said, well, in fact, now we are working with a financial use case, a use case that was being done in the financial sector. We are now applying it into our energy company. So it can be so broad and so wide. So there is so many things to explore, which makes it, of course, very very nice and interesting. Now, the question is, when will this happen? Now, you already know probably IBM is very active in the space, and since 2016, it already started. So you can access our system since 2016. This is our roadmap. So since 2016, Quantum is available through the cloud. And as from then, we really have put a roadmap publicly available. This is something that we normally not do in IBM, but we really wanted to do it just to show we are really investing in it. We believe in it, and we are convinced that this is the future. And we are investing at different levels. First of all, there is, of course, the hardware. The hardware part, it's evolving fast. We currently have the 156 Heron computer chip, quantum chip. This is something that is, like I said, moving fast. One of the things that we are looking at is now to couple different chips so that we can scale that way. So that's the hardware part. So we of course always need to see, can we scale? So we need the number of qubits, of course. And by connecting, we have a modular system. So by connecting the chips, we target to scale. But we also need to, of course, the quality of the chip is, of course, important. And then, and also the speed. What are you with the computer when it's very slow, a quantum computer when it's very slow, and you need to do all this simulation. So those three elements at the same time are being looked at. And it's not just one or two, you really need those three characteristics. Now, it's not only the hardware. As important is, of course, the software. And we are using Qiskit, which is based on open source technology. But we are investing hugely there because we want to make it more easy for the end clients to access the system. We are also infusing some AI in there. Also, again, to make it more easy for the developers. So we include Watson Code Assistant. And then next to the Qiskit part, there is, of course, also the application part. So that's also something where we want to focus on. By the way, we have also functions. Functions is, in fact, startups that have an end-to-end solution that you can integrate in your development process. It makes it easier, faster for the developers. So it's a kind of plug and play within their development chain. And those functions are at different levels. It can be a chemistry function. It can be more focusing on error correction. So different startups that are embedded as a function into our Qiskit platform. And we see more and more startups reaching out to us because they want to become also a part of that platform, because finally we want to also help the startups to monetize their solutions, so that this whole ecosystem can grow. It's not only about IBM, but it's also about startups. It's also about the industries and so on. So this is the roadmap. Now, what we do already announced is that in 2029, we announced the error-corrected quantum computer. It's called Starling, and it will have 200 logical qubits and 100 million gates. So you know that the gates is a depth, which is important for the more complex problems. Now, we also say, should we wait until 2029? Because sometimes we get that question. Of course, not, because there is so much to explore. You need to build your skills. So you should certainly not wait until 2029. because by then, that point, it will be too late, because we see more and more organizations that are already investing in it, and we see also much more patents that are being requested. So, and you know, patents, once you have a patent, you're protected. So it's important to already look into it now. We also see that it's a kind of change management. So don't think really kind of classically, but try to think in another way. And also that requires a change management and really understand what is now a quantum use case. Is this a good one or not? Because not every use case is a good one for quantum computers and so on. So that's why we say start now. And that's also why we see that more and more noise is being made, and more interest is, of course, also in quantum computing. So 2029 is one milestone, but there is another milestone, and that is 2026. And there we are confident that we will see the first demonstration of quantum advantage. Quantum advantage, our definition is that we can do something faster, cheaper, or better than classic computing. So that's where we think that that we will see already 2026, which is, of course, quite quickly, because 2026 is not far away. So less than 1 year, we will be in 2026. And we believe that's our first thinking, that it will be in more in chemistry. Probably the first quantum advantage will be more in a lab before really into a real world use case. But you know, once it's in a lab, then it will go fast, very fast. So that's where we are working very hard in Japan, for instance, with RIKEN. RIKEN is a research center in Japan where we are working very closely with. Now, we also say that quantum computing is not just a separate pillar, but it should be integrated. It should be integrated in your architecture. And we say that also the integration of classic or HPC and quantum computing is important. And that's why we have also been investing hugely with several of our partners. RIKEN is one of them in Japan, but also STFC in UK. We are working on it with RPI. RPI is a university in New York. They're also looking at this integration of classic and quantum computing. And there we really need to look at a kind of, it's mainly at the software level and at the scheduling level. How can we more smoothly send some jobs to our classic computing, the HPC, and maybe some of them to quantum computing. So they were also looking at the Slurm. How can we better integrate all those things with the scheduler. So that's more about the integration, classic quantum computing. Now, as I said, it's all about early adopters, because we see that early adopters, and this is not IBM saying that, this is Boston Consulting Group, we estimate that they will capture 90% of the value, which is huge. And therefore we say, if you're not starting now, it will be very difficult to catch up. So think about if you find a material and you're depending for the raw material from a country where there is maybe war, or it's becoming very expensive to import, and you are really dependent on it. But you could replace it. You find a solution to replace it by another material, and your competitor doesn't have that material. So then you really build that competitive advantage. So therefore, it's really important that you also look, that you start looking into now. Now, IBM is investing hugely in education. And I think if we talk about universities, education is very, very important. If you look at and really building that ecosystem. So first of all, within our ecosystem, we have now in the meantime more than 300 members. these are universities, but also industries. It can be startups. So it's really a mix of everything. And we have more than 600,000 users now. So I think it's also good to understand the number of papers. And I know that companies and also PhD students, they are working on papers. So it's very important also to focus on that one. We have now more than 700,000 courses, and we really look so much publicly available. So we really urge students or even companies to, it's really available, publicly available, to look into those courses and start building your skills. And it's not only those courses, but you can also have badges. And I know that's important also to get this badge or certifications. So for developers, we have certifications. So I think that's also important to look into it. By the way, if you have students, I think it's important to know that there is a really shortage of skills and quantum developers and quantum skills. So always interesting if you don't know what to do, to change your mind and go into quantum. Just a few examples of companies that we're working with to give you ideas. So you can see that it's not only at the industry level, but also it's banks, but it's also GSI, so service integrators. It's lots of universities you can see here. It's across the world. CTU is, for instance, in Czech Republic. FreeMind is in Romania. Bosch is a company then in Germany. You have lots of startups. You have US companies. Pink is in Canada. LTR Mindtree, TCS, they're all worldwide. So many are already part of our ecosystem, which is good, because what do we do with this ecosystem? We really organize events. We bring them together. We always say, share the good, the bad, and the ugly, because we need to learn from each other. This is emerging technology. It's very important that we learn from each other, that we share. And that is what we are doing in this ecosystem. So that's also what I wanted to say. So we have a lot of quantum learning. Some things are publicly available. If you just Google on YouTube IBM Quantum, you can see lots of videos. But we also have a quantum challenge. We have the Fall Fest, of course, not to forget, Brian. But we also have the Qiskit Global Summer School. So every year, and I really urge you also to be part of it, every year we have a Qiskit Global Summer School, 2 weeks. This year we had 8,000 participants, and we had to stop because too many people were registering. And also there, I think it's important to understand that that it's really about learning, and you get also a kind of badge certification that you have attended it. And it's really given by IBM Quantum researchers and experts internally, but also external speakers. So I think that's really an important one. But like I said, it's like registering for a big concert or festival where you need to be behind your laptop and making sure that you have a ticket. So yeah. Then we have lots of quantum innovation centers, and a quantum innovation center is really where we bring together 4 pillars. First of all, we focus on education. We focus on the ecosystem development. We help you developing that ecosystem. And in the middle, you have a kind of a hub where we build around it. For instance, we have a quantum innovation center in South Africa. Now it is with the HPC Center. It used to, but it's working together with Wits University, with Stellenbosch, and so on. So I think that's really interesting, because we also try to include now some industries, because the industries, they have the challenges, and then working together with researchers and universities, PhDers, so that is, and getting access to our systems. I think that's really where it becomes interesting. And of course, we want to grow across in Africa. I think it's important to provide as much as access as possible to the community. You can have easily access to through the cloud, but I just want to mention that we also have clients or partners who say we really want a system on site. And that's also what we have. We have one in University of Tokyo. We have one in Cleveland Clinic. Cleveland Clinic is focusing on it's a private clinic, but they also have a huge research center in life sciences in the US. And it's cool because the system is located in their cafeteria. So that's really cool. And they do events around it. It attracts lots of talents. So that's really cool to see. Pink is in Canada. So they also have a system there. Rensselaer Polytechnic is RPI. It's in New York. We have Yonsei University in South Korea, where they have a system. We have Kobe, that's Riken. That's also one in Japan. So they have two in Japan, two systems in Japan. And yesterday we launched. It was an inauguration in Basque, which is in Spain, in northern Spain. So that was in San Sebastian. So that was cool. Lots of it was the ribbon cutting. Lots of politicians there. So they're really doing very well there. They grow their ecosystem. They're doing so well in research now. Just by having this system, it attracts so much talent. And once I asked them, why do you want a system? You can have cloud access. But they said, yes, we want to attract talent also, but not only from Spain, but also from southern Spain, southern of France, from Italy. And you can see this network and community really growing. Chicago, we are building this as we speak. We are building, so they ordered also a system, and we are building that system now. And India, they also have one, ordered one. So we are also building that, and we will normally install that one in Q1. Then, but you can easily access through the cloud, like I said, and there are different kinds of access. Just that you know, you don't need to spend a lot of money. You can already access our systems for free. We have an open plan for 10 minutes a month. You can easily access it. But you also have a flex system if you want to do more than that. We have the premium plan if you really want to do some project work. And pay as you go. So we have so many different options. And if you really want to work on a project together with us on a use case, we can also collaborate together. So like the needs, we can work together. Now, this is about quantum, bringing quantum to the world. Of course, and this is not a topic, but just one or two slides on quantum safe. We all know that there can be some bad actors. There are always bad actors, and therefore we need to make sure that we also look into what can we do, because what we think is that today's classical security protocols can be obsolete tomorrow, and that it can be dangerous, of course. And that's where we say, okay, we need to start protecting ourselves. And you know that we have the prime factors where P multiplied by Q is easy. That's much easier, the result. And 3 multiplied by 5 is 15. That's easy. The other way around is more difficult. Certainly, if you have large bits figures, so then it becomes very, very difficult. And the expected computation time is millions of years if you have to do it with classic computers. Well, if you say with Shor's algorithm, and that is the quantum algorithm, you could break this security protocol in hours. And that's when it becomes very dangerous. And then you can say, okay, but therefore you need these large quantum computers, which is true. But what bad actors can already start doing now is they can say, okay, we already gather your information and we keep them. And once we have the large computers, we will use the quantum algorithm, Shor's quantum algorithm. So that's where it becomes dangerous. And therefore, we just want to, it's not the goal of this talk, but we just want to say, okay, be aware that this exists. So, and in 2015 or so, there was a kind of, it was a kind of RFP, a tender that was written, I think it was by NIST, where we say, okay, who can write an algorithm that protects us against these large quantum systems. And also IBM we've worked on this for 4 years, and we had 4 algorithms where we came out with, and 3 of the 4 has been selected by NIST, and 3 of the 4 were from IBM, and the 4th one was from another person, but now he's also part of IBM. So, but this way we're all from IBM. So I think it's good that at least it exists, and slowly we can start protecting our environment. And we do have some. This is not quantum computing. This is really a kind of shelf where we say, okay, where are the vulnerabilities within your company or within your environment, and can we at least already start prioritizing them? And then we have the quantum advisor. This is just software. Then we have the quantum advisor who says, okay, let's start with this and this and this, because those are the most vulnerable ones, and then see how we can remediate them. So it's just starting that journey already to become also quantum safe. But of course, this is a journey that will take years, but it's good to at least think about it. So, and that's what I also wanted to say to everybody. So get certainly to the universities and to the students, but also to the workforce within the companies. Upskill in quantum, start building your skills, engage in the system, in the ecosystem, and just try it out. It's for free. You can access for free, and just try it out, I would say. And then begin your journey to quantum safe if you can. So that's what I wanted to share here to the teams. I don't know if you have questions specifically related to this.
Thank you so much, Petra. Any question for Petra? Now is
Thank you,
the
Annemiek,
best
for
time to
being
ask.
here. Yeah, thank you so much for being here. And I'm here. I'm around, so I'm always happy to be here or to connect. Just reach out to me.
Is there someone with a question for Petra before we wrap it up? Thanks so much. That was a concise presentation.
Thank you. I hope it was helpful. Thank you so much.
Greg, do you have a question for Petra?
If not, I want to thank you, and I'm going to the next meeting. Sorry for that. But like I said, you can always reach out to me. I'm traveling a lot, so I was recently in Rwanda, by the way. So that was the Indaba community AI, and there was also one day on quantum. So that was really, really interesting. So maybe next time I come to Kenya.
All right, thank you.
Thank you so much. Bye-bye.
Greg, can you wrap it up for us? Can you wrap the day for us with if you have something to say before we quit?
I'm sorry, you asked me to say something?
Do you have something to say before we quit?
I would like to elaborate on one thing that Petra said. She said that 2029 is too late. Is the way it was worded could go across a few different ways, but what she was saying is for companies to wait until 2029 is too late, is what she was saying. And that's something that many of us are trying to share with everyone. And so I fully agree with what you're saying, that companies need to start looking at developing quantum technologies presently. In any case, I want to thank all of you for having me come in to speak as well. And so best of luck with all of it. Sounds like many of your students, and so good luck with all of your studies and so on.
All right. Okay. Thank you. And bye-bye, everyone. We'll catch up next time. Bye.